Hello there, and welcome. Tonight, we'll wander into a scale that dwarfs every measurement we've ever known. A universe so vast that galaxies become dust, distances lose their meaning, and time stretches into something soft and almost fluid. We'll explore 100 mind-bending truths from the size of stars that would swallow our solar system whole to filaments of galaxies spanning billions of light years. You don't have to grasp it all. Just float with it. The cosmos doesn't rush, and neither should you. Let the enormity of it all make your own worries feel lighter, smaller, easier to set down for the night. And while you're settling in, before your eyes grow too heavy, I'd love it if you gently tapped subscribe or pressed the little hype button YouTube recently added. It's a small click, but it helps keep these experiments and explorations orbiting out into the algorithm. You can also leave a comment telling me where you're listening from and what time. It is in your corner of the night. It's oddly fascinating to see where people are drifting off with us, scattered across the world like stars across the galaxy. Now, take a deep breath, let your day drift away, and let's travel together into the quiet corners of the universe. At the smallest scales we can imagine, the universe begins to lose its familiar shape. The things we think of as solid, ordinary, or dependable start to blur and shimmer, as if reality itself is made from something finer than dust. Quarks and leptons, the tiniest known building blocks of matter, drift through this hidden world. They do not behave the way larger things do. They flicker in and out of certainty, suspended in a place where position and motion cannot both be known. A quark is so small that trying to picture it in your mind is like trying to hold the edge of a dream. It isn't an object in the way a pebble or a grain of sand is. It is more like a pulse, a vibration, a pattern of energy that gives shape to the particles we're familiar with. When you look closely enough, even the things you thought were indivisible become a kind of whisper. Leptons, such as electrons, behave just as strangely. They circle atomic nuclei, not like planets around a star, but like a probability cloud, smeared across a region rather than occupying a single place. Their nature is not in the location they hold, but in the space they could hold, a soft halo of potential shaped by quantum rules. When you shrink your attention down to their scale, space stops feeling empty and becomes something dense with possibility. Every inch of it is alive, with tiny fluctuations and the restless movement of particles that never fully settle. There are no edges here, no clean boundaries. What we call smallest is itself a shifting idea, because each layer of magnification reveals a structure more delicate than the last. The Planck length sits even below that, a scale so unimaginably tiny that it lies far beyond the reach of our instruments. It is the limit where space and time themselves begin to unravel. If you could zoom in by a factor of 10 again and again, shrinking past atoms, past quarks, past anything we have ever measured, the Planck length is where your journey would meet a kind of cosmic threshold. Below this distance, the very concept of size ceases to make sense. Space becomes grainy, like a mosaic made of pieces too small to distinguish. It's the point at which the fabric of reality is thought to be threaded with loops or vibrations, depending on which theories you follow. Whatever those structures are, they mark the bottom floor of the universe as we understand it. It's not just small, it's the scale at which the rules of geometry, motion, and continuity begin to fall apart. Physicists sometimes describe this deep foundation as quantum foam, a restless sea of tiny fluctuations bubbling at the smallest scales. It's a beautiful phrase for something wild and frenetic. Instead of a smooth, continuous surface, space becomes a patchwork of surfaces that appear and vanish instantly. Ridges rise and fall, pockets of energy spark into existence and dissolve before they can be recorded, and the very shape of space-time trembles with constant motion. Nothing is still here. Even emptiness is busy. The foam is a reminder that the universe is not built like a calm, steady structure, but like a living field of activity, its foundation humming with a quiet kind of turbulence. If you could somehow drift through it, it would feel less like falling through space and more like drifting through a river whose waters churn in unpredictable swirls. Within that foamy landscape, virtual particles appear and disappear, flickering in and out of existence in timescales too short to notice. They do not persist long enough to be called true particles, but they influence the world around them all the same. Their brief existence affects the forces that bind atoms together, the energy within empty space, and even the motion of real particles nearby. It is strange to imagine a universe where things can exist without fully existing, but this is the nature of the quantum world. These ghost-like particles rise from fluctuations in energy, exist for the blink of an instant, and then vanish again, leaving behind faint traces of their presence. Everything you see, every object you touch, is shaped by interactions with things that flicker too quickly to ever be directly observed. When you build from these ingredients quarks, leptons, virtual particles, and the trembling foam they form the atoms, molecules, and living worlds we know. But beneath it all lies an unavoidable truth. The universe may not allow infinite divisibility. There may be a final floor, a smallest possible unit of length or time, a boundary beyond which even imagination cannot travel. As we probe deeper, our measurements themselves become part of the problem. The act of observing at such small scales injects energy, distortions, and uncertainty. Light, which we use to see, becomes too coarse a tool. Forces that are gentle at large scales become overwhelming here. The closer we look, the more the image slips away. This limit of divisibility is humbling. It suggests that the universe holds on to its deepest secrets behind a curtain woven from probability and motion. We are allowed to see hints, patterns, and silhouettes, but not the full shape. The smallest things we know are not objects but rules, not places but possibilities. They are suggestions quietly influencing the formation of stars, cells, and thought itself. When you rest tonight, consider that every part of you is made from these trembling foundations. Your bones, your skin, your breath. All of it is assembled from particles that refuse to stand still. You are built from things that dance in darkness, flickering in and out of certainty, shaped by distances so small they may not even exist in the way we understand. Sometimes, the greatest comfort in thinking about these scales is the realization that nothing in the universe is truly solid or rigid. Everything is composed of movement, vibration, and probability. Even the quietest moment in your day is threaded with the gentle shiver of quantum activity. The smallest things we know are reminders that existence itself is woven from a fabric more delicate than any material, a fabric that hums and fluctuates beneath every heartbeat. You are part of that fabric, connected to a world so small it escapes sight, but never influence. As you drift further into this journey, you carry that truth with you. The universe begins in whispers so faint they almost vanish, yet from them, everything else unfolds. Atoms exist in a realm so small that even the smallest objects you've ever held feel impossibly huge by comparison. An atom is mostly space, a ghostly structure with a dense nucleus at its center and electrons drifting in wide, hazy orbits around it. If an atom were the size of a football stadium, the nucleus would be a grain of rice sitting at the center, while the electrons would swirl somewhere near the outer walls, smeared across the air in a blur of probability. The rest would be empty, so much emptiness, in fact, that the solidity you feel when you touch something is not solidity at all, but the quiet resistance of electric forces meeting one another. At this scale, matter loses its familiar firmness. It becomes a delicate architecture built from space and energy, held together by invisible threads. Though atoms are unimaginably tiny, they come in different sizes. Hydrogen, the simplest and smallest atom, has just a single proton and a single electron, making it the lightweight of the periodic table. Larger atoms like cesium or xenon have far more complex shells, with electrons arranged in layered clouds that stretch out farther from the nucleus. The difference in size between atoms is astonishing when compared to their shared smallness. A helium atom is nearly twice the size of a hydrogen atom. A cesium atom is dozens of times larger still, and yet all of them are so small that billions could sit on the head of a pin while leaving room to spare. When you zoom in far enough, measurement loses the sense it has at larger scales. Everything becomes a comparison of something tiny to something even tinier, and the gaps between them begin to feel surreal. At this level, electrons do not orbit their nuclei like planets or marbles on tracks. Instead, they form diffuse clouds regions where the electron might be, drifting in patterns shaped by quantum rules. These clouds are not rigid boundaries, but shifting landscapes defined by probability. In some places, the cloud thickens. In others, it thins, like layers of mist gathering around an invisible center. The shapes they take, spheres, dumbbells, rings, are not acts of design, but the natural solutions to the equations that govern their motion. Each cloud is a quiet map of where an electron prefers to reside, a soft halo around the heart of the atom. You never truly see the electron itself. All you can detect is the faint outline of its presence, as if the universe only allows us to glimpse the shadow of a deeper truth. When atoms join together to form molecules, the scale shifts again. A molecule is not just a gathering of atoms, but a tiny constellation of bonds and angles, a geometry of forces connecting nuclei across astonishingly small spans. A single water molecule is less than a nanometer wide, its 3 atoms bent into a gentle V shape that gives water many of its unusual properties. Larger molecules, like simple sugars or amino acids, grow into more intricate shapes, spirals, chains, branching clusters that interlock like pieces of a puzzle. And yet even these structures remain so small that billions of them are needed to form something as simple as a drop of liquid. As molecules grow in complexity, they begin to build the frameworks of life, proteins folding into elaborate shapes, DNA coiling into long ribbons. These molecular frameworks shape everything you are, every process that happens within you, every thought that passes through your mind. What's most remarkable about molecules is how much space lies between the atoms inside them. Even when billions gather into a tangible substance, the emptiness remains. The chair beneath you, the air you breathe, the skin on your hand, all of it is composed mostly of space. If the atoms that make up your body were somehow compressed until all the empty space vanished, you would be smaller than a grain of salt. This isn't metaphor or exaggeration. It's a quiet, humbling truth about the nature of matter. Solidity is an illusion created by forces acting at unimaginable speeds and scales. The world feels full and firm because your senses cannot perceive the ocean of emptiness threaded through everything. Inside your own body, distances that feel insignificant at a human scale become vast stretches at a quantum level. Within each cell, molecules drift and collide in a fluid dance guided by thermal motion. Electrons move so quickly and unpredictably that their paths cannot be traced, only approximated through clouds of probability. Signals travel through these tiny regions as vibrations and exchanges of energy. Every process that keeps you alive, breathing, thinking, sleeping, dreaming, depends on events happening in spaces millions of times smaller than the width of a hair. Within these microscopic arenas, distances that seem impossibly small contain entire landscapes of activity, invisible theaters where particles interact in ways that shape the world you know. Quantum distances inside you are not like any distances you've walked or measured. At this scale, rules change. Particles can tunnel through barriers that should be impenetrable. Electrons can be in multiple states at once, until they are observed. Bonds form and break with energies so small they escape notice, yet their effects ripple outward, influencing everything from muscle contractions to memory formation. Moments pass here faster than thought, faster than the beat of a hummingbird's wings, faster than any rhythm you could hope to feel. These distances are not just the space between molecules. They are the space in which life happens. When you think about the scale of atoms and molecules, it can be easy to imagine them as small components in a larger structure, like bricks in a wall. But they are not bricks. They are more like notes in a song, fleeting, dynamic, shaped not by their size but by their relationships. The molecule that forms when oxygen and hydrogen bind becomes something new, something neither atom could be on its own. The pattern of electrons swirling through its bonds determines how it behaves, how it bends, how it interacts. Each tiny structure contributes to a larger harmony, a whole made from pieces that are themselves only patterns of energy and space. The landscape inside you is a reminder that reality is layered. Your senses perceive one version of the world, solid, continuous, predictable. But beneath that surface lies a terrain woven from probability, distance, and emptiness. The molecules that compose you are drifting in a sea of motion too small to see, yet their behavior defines every breath, every heartbeat, every dream. This tiny world is not separate from you. It is you. And as you drift further into this journey, remember that within every moment of your life, quantum spaces are opening and closing inside you, shaping your existence one invisible distance at a time. When you think about your place in the world, it's easy to imagine yourself as ordinary in size, neither particularly large nor especially small, just a person moving through familiar spaces. But compared to the tiny world that operates beneath your senses, you are a merry, towering giant made from countless microscopic structures working together in silence. Each cell inside you is its own small universe, a self-contained system so minuscule that millions could fit on the tip of a needle. Most of them are only a few micrometers across, smaller than the width of a strand of hair. Yet within those tiny boundaries, they carry out the full choreography of life. They swallow nutrients, repair damage, communicate through chemical signals, and replicate themselves with astonishing precision. A single cell seems impossibly small until you remember that your body contains trillions of them, weaving you together one soft thread at a time. Inside nearly every one of those cells lies DNA, a molecule so long and intricately folded that if you were to stretch the DNA from a single human cell into a straight line, it would reach about 2 meters. 2 meters, hidden inside something too small to see without a microscope. To fit such a length into a microscopic space, the DNA coils and loops, wrapping around proteins like a tightly wound rope. The entire molecule folds again and again until it forms condensed structures that slip neatly inside the nucleus. If all the DNA in your body were laid out end to end, it would stretch billions of kilometers, enough to reach the sun and return many times over. The idea that a human being carries an entire galaxy's worth of coded information in microscopic spirals is both humbling and strangely comforting. It means that even the smallest components of your being contain a history far older than you are, written in a language of molecules and bonds. The microscopic world around you is populated by creatures even smaller than your cells, living in numbers too large to imagine. Microbes, bacteria, archaea, and tiny single-celled organisms exist everywhere within and around you. Some are only a fraction of a micrometer across, so small that thousands could drift through the eye of a needle without touching its edges. These organisms live on your skin, in your digestive system, and in the air you breathe. Many help you survive, breaking down food, producing vitamins, or defending you from harmful invaders. Each microbe moves through its world with a kind of slow, patient intent, drifting through spaces so narrow that your smallest features seem enormous. To them, a human fingerprint is a mountain range, a bead of sweat, a vast ocean, a single eyelash, a fallen tree. Even smaller than most microbes are the viruses, though they exist in a gray space between life and non-life. Many viruses are tens of nanometers wide, so small that they cannot be seen with standard microscopes. They operate not by living fully on their own, but by hijacking the machinery of cells, slipping their genetic material into the delicate interior and using the cell's own tools to replicate. Whether they are considered alive or not, their scale is extraordinary. A reminder that life, influence, and consequence do not require size. They drift through the microscopic realm like tiny coded messages, waiting for the right door to open. Within your bloodstream, red blood cells flow in dense, steady rivers, each one shaped like a small disc with a soft concave center. They are about 7 or 8 micrometers wide, large compared to bacteria but still far too small to see with the naked eye. These cells carry oxygen through your body, delivering breath to every corner of your tissues with a rhythm so consistent you rarely notice how much depends on their motion. A single drop of blood contains millions of them, moving in currents as they tumble through arteries and veins. Their size is small enough to navigate the finest capillaries, microscopic pipes that twist through your organs like threads. The pathways they travel are so narrow that some red blood cells bend themselves in half just to squeeze through. White blood cells, though fewer, are larger and more irregular in shape. They patrol your body like silent guardians, expanding and contracting as they push through tissue, hunting for signs of infection or damage. Compared to microbes, they are giants, but compared to you, they are as small as dust motes. Their scale sits somewhere between worlds, not quite large enough to be seen, but vast enough that they move slowly and purposefully through the bloodstream. These cells are part of your defense, standing ready in a world where threats are invisible to you but enormous to them. When you compare yourself to the microscopic world, the contrast becomes astonishing. You are built from structures that are themselves composed of smaller structures, which are in turn built from atoms arranged in patterns too small to conceive. Every gesture you make, every breath you take, is powered by events happening in distances so tiny they slip between the cracks of your imagination. If a single human cell were scaled up to the size of a house, a strand of DNA inside it would stretch from room to room, and a virus drifting nearby would be no larger than a grain of sand. In this scaled-up view, your own form becomes a bustling city made of machinery so intricate that even its smallest parts contain still smaller worlds. Consider your height in terms of microscopic distance. A person who stands 1.8 meters tall is roughly 100 billion times taller than a bacterium. To a microbe, you are not just large, you are a landscape. When you place your hand on a surface, millions of microscopic organisms see a shifting wall of peaks and valleys descending toward them. When you speak, your breath becomes a storm that pushes microbes across vast expanses. The scale difference is so vast that the two worlds barely touch in perception, even while occupying the same space. This divide in size shapes how reality feels to you. You move through your life unaware of the molecular machinery that keeps your heart beating, or the swarms of microbes that help digest your meals. The microscopic world operates in silence, too small to interrupt your thoughts, yet without it, nothing familiar would exist. You are a towering being made from the smallest components, your body a cathedral built from countless invisible bricks. In every blink, the microscopic world works tirelessly beneath the threshold of your senses, keeping you alive, balanced, and breathing. The human scale feels natural because it is the only one you inhabit. But when you peer downward into cells, molecules, and microbial lives, you begin to see that size is relative and significance is not tied to magnitude. The tiniest processes within you, happening in spaces far smaller than the width of a hair, shape your experiences, your memories, your emotions. You are vast compared to these small realms, yet utterly dependent on them. And in that balance between small and large, you find a quiet truth. Your world is built from wonders you will never see, but that follow you, support in you, and whisper through your existence in ways too small to notice. Across the surface of our planet, the world you walk through each day feels immense and varied, yet it represents only a thin and delicate shell wrapped around a far larger sphere. Mountains rise like ancient monuments, oceans sink into deep blue basins, and continents drift slowly across molten rock beneath them. But even the tallest peaks and deepest trenches exist only within a narrow band of Earth's crust, a fragile layer compared to the vastness of the planet below. When you stand on the shore of an ocean or at the foot of a mountain, you are standing on a membrane so thin it would be hardly more than a coat of paint if Earth were the size of a familiar globe. And yet, within this thin surface, the planet contains some of the most dramatic landscapes imaginable, carved by time, pressure, and the quiet forces that shape worlds. The ocean, which seems endless from the shore, hides depths that push far beyond human intuition. The Mariana Trench plunges nearly 11 kilometers beneath the surface, a chasm so deep that if Mount Everest were placed inside it, its peak would still lie underwater. At those depths, pressure becomes crushing, the weight of the entire ocean stacked overhead like a mountain of liquid. Light cannot reach that far, and the water becomes ink-dark, silent, except for the faint creaks of shifting rock and the soft movements of creatures that have adapted to the crushing environment. Yet even this incredible depth barely dents the surface of the Earth when compared to the whole planet. The deepest place in the ocean is only about 1/1000th of the Earth's diameter. To the planet itself, this trench is just a shallow scratch in its surface. Above sea level, mountains rise in slow, steady ways built over millions of years by the collision of tectonic plates. The Himalayas, the Andes, the Rockies, stark reminders of the planet's restless interior. Mount Everest is the tallest above sea level, towering nearly 9 kilometers into the sky. But compared to the size of the Earth, that height is almost negligible. If Earth were shrunk to the size of a large sphere you could hold in your hands, the tallest mountains would be nothing more than small imperfections on its surface. Even so, standing atop one of those peaks, with clouds drifting beneath you and the air thin and sharp, feels like touching the edge of the world. Other planets show us what true extremes look like. On Mars, the volcano Olympus Mons rises to a height that dwarfs anything on Earth, reaching nearly 22 kilometers into the sky and spreading across a region the size of a small country. Its slopes are gentle and wide, the result of a different gravity and crust structure than Earth's. It is so large that someone standing on its peak would not even be able to see its base. The curvature of Mars would hide it. Compared to this titan, Earth's mountains seem modest, shaped not by lack of strength, but by the planet's constant geological churn. Earth's crust shifts, folds, and recycles itself more vigorously, preventing mountains from growing as immensely as they do on quieter worlds. The comparison reminds us that landscapes reflect the inner lives of planets, each shaped by forces unique to its history. Despite how rugged the Earth's surface appears, its crust varies greatly in thickness. Under the oceans, it is thin, only a few kilometers deep, stretched by spreading ridges, and cooled by constant contact with the sea. Under continents, the crust thickens dramatically, especially beneath towering mountain ranges where the weight of rock presses downward and the deeper layers respond by swelling upward in return. Some continental crust beneath the Himalayas exceeds 70 kilometers in thickness, a complex weave of rock and heat built from countless collisions. Yet even this thickest crust is just a thin outer rind compared to the planet's radius. The mantle beneath it is vast, stretching thousands of kilometers downward into dark, slow-moving currents of molten rock. As you move through your daily life, it's easy to think of the world as flat because you only see a small piece of it at once. But Earth's curvature is always present, gently bending the horizon and shaping the illusion of flatness. When you stand on a beach, The horizon is only a few kilometers away, limited by the curve of the ocean. Ships vanish hull first as they travel outward, slipping below the line where sky meets water. From high altitudes, the curve becomes clearer, a soft arc framing the edges of clouds and land. What feels like a flat surface is actually a portion of a massive sphere, so large that its roundness becomes invisible from the ground. You live on the surface of a colossal globe, but the scale makes it easy to forget. Earth's radius, about 6,371 kilometers, defines the shape of the world beneath your feet. This distance from the center to the surface is enormous compared to anything we experience directly. If you traveled downward through the Earth, you would pass from the cool crust into the hot, dense mantle, and then into the molten outer core, where metal moves like thick liquid. Deeper still lies the inner core, a solid sphere of iron and nickel, glowing with heat despite the pressure that keeps it frozen in place. All of this fits inside the radius of the planet, stacked in layers like the strata of an ancient world. And yet, the life we know flourishes only on the outermost edge, a thin layer of soil, rock, and water that wraps this vast interior. When you step back and imagine the Earth not as your home but as a planetary body, the landscapes you know take on new meaning. The tallest mountains reach only a tiny fraction of the planet's height. The deepest trenches barely scratch its surface. Even the oceans, which cover most of the world, fill only the shallowest portion of its outer shell. The planet's true scale lies beneath, in the immense distances that stretch from crust to core and from surface to center. Yet the smallness of these surface features doesn't diminish their wonder. Instead, it highlights the delicate balance that makes them feel so grand to us. Mountains tower because we are small. Oceans feel endless because we can't see across them. The curvature of the Earth hides itself because the world is far larger than our senses can grasp at once. Our scale defines our perception, and within that perception, the planet becomes a place of vast horizons, deep waters, and sky-piercing peaks. In the end, Earth's greatest beauty may lie in the way it bridges, scales the immense and the intimate, the planetary and the personal. From space, it is a smooth blue sphere, wrapped in a thin atmosphere. Up close, it is a world of rugged coastlines, quiet valleys, towering ridges, and deep, hidden trenches. Every feature that feels monumental to you is just one part of a landscape shaped over millions of years, resting lightly on the surface of a planet whose true depths remain largely out of reach. As you drift through the quiet of this moment, remember that you stand on a world larger and more intricate than it appears, a world where size and scale shift with every step you take and every horizon you chase. When you look at the planets of our solar system, it's tempting to think of them as a matched set spheres drifting around the sun, each one following its path in quiet procession. But the scale of these worlds varies so dramatically that comparing them is like comparing raindrops to storms. Mercury, the smallest planet, is barely larger than our moon, a scorched sphere that could disappear comfortably beneath the shadow of the gas giants. From end to end, it spans just under 5,000 kilometers, small enough that a cross-country journey on Earth would cover a noticeable fraction of its diameter. Pluto, though no longer considered a major planet, is even smaller still, a frozen pebble drifting in the darkness beyond Neptune. And then there are worlds like Earth and Venus, siblings in size and density, similar enough that early astronomers once imagined Venus as a twin world shrouded in cloud. Their scale feels familiar, manageable, human in its proportions. But once you move beyond the rocky planets, the scale shifts abruptly. Jupiter, the largest planet in the solar system, is so massive that more than 1,300 Earths could fit inside it, and yet it is composed mostly of hydrogen and helium gases, compressed by gravity into layers so deep they blur the line between substance and pressure. Its diameter stretches nearly 140,000 kilometers across, a size so immense that if Jupiter were hollow, every planet in the solar system could fit inside with room to spare. Saturn, though smaller, is still vast enough to dwarf every terrestrial world many times over. Even Uranus and Neptune, often overshadowed by their larger neighbors, are giants in their own right, each more than 4 times wider than Earth. Standing on Earth and looking at the planets through telescopes, it is easy to forget how tiny we truly are compared to the enormous globes drifting alongside us. Inside these giant worlds, the layers become stranger and more exotic with depth. A gas giant's atmosphere appears soft and swirling from the outside, with storms curling in colorful bands, but beneath the clouds lies a world of crushing pressure and heat. In Jupiter, the gases compress into a superheated ocean of metallic hydrogen, a strange substance that forms only under intense pressure. Electrons move freely through this metallic sea, creating deep, powerful magnetic fields. Farther inward, the temperature rises so high that hydrogen atoms lose their structure, forming an immense, shining interior. The core, if it exists as a solid object, may be a dense mixture of rock, metal, and exotic forms of core, matter unlike anything we experience on Earth. These layers do not behave like the crust, mantle, and core of terrestrial planets. They dissolve into one another, blending gradually from atmosphere to ocean to unrecognizable depths. The distances between planets are as staggering as their diameters. The Earth orbits the Sun at an average distance of 150 million kilometers, a span so vast it becomes a kind of emptiness between worlds. Mercury, closest to the Sun, circles at about 1/3 that distance, moving swiftly along its tight orbit. Venus sits between us and the Sun, close enough that its phases can be seen like those of the Moon. But once you pass Mars, the gaps widen dramatically. The asteroid belt spreads out between Mars and Jupiter, its rocks drifting through a space so large that they are separated by millions of kilometers. Beyond Jupiter, the distances grow even more immense. The outer planets orbit so far from the Sun that their years stretch into decades or centuries. Neptune, cold and blue, completes a single orbit in about 165 Earth years. The Sun, which feels like the center of everything from our perspective, becomes only a distant point of light from these remote worlds. Temperature adds another layer to the scale of planets, shaping their surfaces and atmospheres in profound ways. Close to the Sun, Mercury swings between searing heat and freezing cold, its temperature shifting by hundreds of degrees between day and night. Venus, with its thick blanket of carbon dioxide, traps heat so efficiently that it becomes the hottest planet, its surface hot enough to melt lead. Earth sits in a narrow band where liquid water can exist, a delicate balance that makes life possible. Mars, colder and thinner in atmosphere, holds pockets of frost and hints of ancient rivers, but the gas giants present their own extremes. Jupiter's upper atmosphere is icy cold, but deeper layers heat rapidly as pressure increases. Saturn's clouds lie far below a haze of methane and ammonia crystals glowing softly in the filtered sunlight. Uranus and Neptune, orbiting in the deep freeze of the outer solar system, reach temperatures near absolute zero at their cloud tops, yet may conceal warm oceans of water and ammonia deep within. Even within a single planet, temperature gradients can be immense. On Earth, the crust remains cool, while temperatures rise dramatically toward the mantle, reaching thousands of degrees in the outer core. The transition from cold surface to molten interior happens across a span of only a few thousand kilometers. On Jupiter, the gradient is far more dramatic, shifting from frigid outer clouds to interiors hotter than some stars' surfaces. Venus maintains a thick global oven, while Mars experiences daily temperature changes so sharp they could crack metal. Across the solar system, heat and cold sculpt landscapes, dictate weather patterns, and determine whether a world is calm, stormy, barren, or vibrant. When you step back and consider these scales, the smallest planets compared to the largest, the internal layers hidden beneath swirling clouds, the vast arcs of orbit, and the extremes of temperature, the solar system begins to resemble a grand mosaic of worlds, each one with its own story, carved in heat, gravity, and time. The human scale fits comfortably on one small world, but the planetary scale stretches far beyond anything you can experience directly. You could travel your entire life and never cross the diameter of a single giant planet. You could send spacecraft into the darkness and still wait years for them to reach the next orbit. The planets circle the sun like immense lanterns suspended in a vast, cold room, their distances so wide that each one becomes its own isolated realm. Yet despite how different these worlds are, they are connected by the same laws of motion, the same forces of gravity, the same delicate balances of heat and pressure. The solar system is a family of extremes bound together by invisible lines, and floating in the midst of it all is Earth, a small planet with oceans, mountains, and air, quietly circling a star at just the right distance. In this immense planetary architecture, we are a single story among many, our world, one chapter in a far larger book. As you drift deeper into this journey, let the scale of the planets remind you of the vastness surrounding us, a vastness that holds each world gently in its orbit, turning silently through the dark. When you look up at the night sky, the stars shimmer as if they are all the same size, tiny distant glints scattered across the darkness. But that illusion comes from distance, not similarity. In truth, stars vary so wildly in scale that comparing them is like placing a candle beside a towering bonfire. Our sun, warm and steady, is only one kind of star among many. It sits in the middle of the stellar spectrum, neither small nor large, a kind of quiet benchmark by which we measure others. Even so, it is enormous by human standards, its diameter more than 100 times wider than Earth's, and its mass so great that it anchors the entire solar system. But out in the galaxy, the sun is simply one example among billions, and many stars differ from it in ways that stretch the imagination. The most common stars in the universe are red dwarfs, smaller and cooler than the sun, glowing softly with light that leans toward the edge of vision. These stars burn so slowly that their lifetimes stretch into the trillions of years, far longer than the current age of the universe. A red dwarf can be so small that dozens could fit inside the volume of the sun, and some are barely larger than Jupiter. They live quiet lives, shining gently and steadily, their surfaces dim and often mottled with magnetic storms. Entire planetary systems can orbit them, basking in the faint warmth of a star that glows more like a smoldering ember than a blazing fire. If the sun were placed among a cluster of red dwarfs, it would stand out as a surprisingly bright and energetic neighbor, almost extravagant in its radiance. But as you move up the scale, stars begin to grow rapidly. Giants, which form when stars like the sun swell during their later stages of life, can expand to dozens of times their original size. A red giant's outer layers stretch outward until the star becomes a bloated sphere of hot gas so wide that its diameter could engulf the orbits of inner planets. If the sun were to become a giant today, it would swell past Mercury and Venus, and Earth's orbit would lie dangerously close to its shimmering atmosphere. Yet these giants are not solid objects. Their expansiveness makes them more like loosely held clouds of glowing plasma, with densities that drop dramatically as size increases. Their vastness comes from the balance between outward pressure from nuclear fusion and the ever-present pull of gravity, a balance that becomes more precarious as they grow. Beyond giants lie supergiants, stars so massive and luminous that they reshape their surroundings. These stars can reach sizes hundreds of times wider than the sun, their surfaces glowing in deep hues of orange or brilliant blue. A blue supergiant burns so fiercely that it consumes its fuel, at a prodigious rate, living only a few million years before collapsing or exploding. Their cores are furnaces of unimaginable intensity, forging heavy elements in layers that resemble an onion's structure. Every second, they release more energy than the sun emits in a year. A supergiant is a star pushed to its limits, its gravity struggling to restrain the power generated within. Even though they burn brightly, their lives are short, shining with enormous intensity before fading into silence. Then there are the hypergiants, among the rarest and most immense stars known. These staggering behemoths can be 1,000 times the sun's diameter. Their outer layers spread so thin that they resemble delicate, glowing shells. The light they produce is so intense that their radiation pressure can push matter away, causing them to shed material in great waves. Their surfaces are unstable, shifting with colossal storms and eruptions that tear at the star's atmosphere. Some hypergiants are so luminous that if they replace the sun, their light would make daylight possible far beyond Pluto's orbit. Their presence challenges the limits of what a star can be, walking the line between formation and collapse. They are cosmic extremes, rare and fleeting, burning with a kind of furious beauty that leaves behind nebulae and heavy elements when they die. All of these stars are governed by mass, the defining trait that determines a star's entire life. A star's mass sets the pace at which it burns through its fuel, the temperature of its core, its brightness, its lifespan, and the way it eventually dies. Too little mass, and a star will never ignite fully, becoming a brown dwarf that glows faintly with leftover heat. Too much mass, and the star burns too quickly, living a short, brilliant life before collapsing into a neutron star or black hole. There is a limit known as the Eddington limit, the point at which a star becomes so luminous that its own radiation threatens to tear it apart. Above this threshold, stable stars cannot exist, because the outward flow of light overwhelms gravity's ability to hold the star together. This limit shapes the upper boundary of stellar mass across the universe and explains why hypergiants, though massive, are rare and ephemeral. The sun sits in the comfortable center of this spectrum, modest in mass and stable in output. It will burn for billions of years, shining steadily and quietly, allowing life to flourish on a small world orbiting at just the right distance. But when compared to the full range of stars, the sun seems almost ordinary. Smaller stars outnumber it by a wide margin, and larger stars outshine it, dramatically, though they do so briefly. The sun's place is neither humble nor grand. It is simply one example of what a star can be, a stable middle ground in a galaxy full of extremes. On nights when the sky is clear, and the stars scatter across the darkness like scattered grains of light, it becomes easier to imagine their differences. Each one glows with its own story, shaped by mass, temperature, pressure, and time. Some are tiny dwarfs, shining faintly in red. Others are immense giants, spreading their radiance across vast distances. A few are hypergiants, blazing so powerfully that they sculpt space around them. Yet from Earth, they all appear as points of light, equal and flat, their true sizes hidden by the enormous gulf of space. As you rest under that sky, you carry the soft truth that the sun, familiar and warm, is only one voice in a vast choir. Some stars whisper, some roar, and some burn with such intensity that their lives are little more than cosmic sighs. But all 8 of them shape the galaxy in their own way, weaving light into darkness, forging elements, and marking time across distances too large to comprehend. In their presence, your world becomes part of something immeasurably larger, a small, bright orbit in a universe filled with fire. When a massive star nears the end of its life, something remarkable happens inside it. The core that has burned for millions of years begins to falter as it fuses heavier and heavier elements. Iron accumulates like a weight that cannot be lifted, halting the processes that once pushed outward with steady warmth. Gravity, patient and relentless, seizes its opportunity. In a fraction of a second, the core collapses inward, shrinking with unimaginable force until it rebounds in an explosion so powerful it briefly outshines entire galaxies. This is a supernova, a cosmic event so vast that even the words we use to describe it feel too small. For an instant, a single dying star becomes one of the brightest objects in the universe. The explosion radius of a supernova expands at speeds that seem impossible. In the first second, material is hurled outward at tens of thousands of kilometers per second, sweeping across the surrounding space like a shockwave of fire. Within hours, the blast has grown larger than entire solar systems. Days later, the expanding shell of gas and plasma stretches across distances that light itself takes hours to cross. Yet, this massive structure is almost ghost-like in density. Its atoms spread thin as it races outward. From afar, it resembles a glowing flower blooming in slow motion, its petals made of gas illuminated by the heat of a dying star. But inside that beauty lies a violence so fierce that no planet or world nearby could hope to survive. Anything orbiting the doomed star is swept away, stripped, melted, or shattered by the expanding inferno. The mass ejected during a supernova is staggering. A star that once held its material together through gravity's grip suddenly flings most of it outward into space, releasing more matter in one explosion than the sun will lose in its entire lifetime. This ejected mass carries the heavy elements forged during the star's final moments: iron, gold, calcium, carbon elements that will eventually drift through space and settle into new clouds of gas, contributing to the birth of future stars and planets. The calcium in your bones, the iron in your blood, the gold in a ring, all of it was once expelled from dying stars in explosions like this. Supernovae are not just endings, they are beginnings, scattering the seeds of new worlds across the galaxy. The light curve of a supernova, a record of its changing brightness over time, tells the story of these cataclysmic events. At the moment of explosion, the brightness surges, climbing to a peak that can rival the luminosity of a galaxy containing billions of stars. Then, slowly, the glow begins to fade. The decline happens over days, then weeks, months, as radioactive elements created in the explosion decay and their energy leaks outward. Each supernova has its own distinctive light curve, shaped by the mass of the star, the speed of the explosion, and the elements released. Astronomers use these curves like fingerprints, identifying the type of supernova and the processes that powered it. Some light curves reveal layered peaks or sudden drops, subtle changes in brightness that reflect the complex physics happening within the expanding cloud. Long before the light from a supernova reaches distant observers, a flood of neutrinos bursts outward from the collapsing core. These tiny particles, nearly massless and able to pass through matter as if it were nothing, escape the star moments before the explosion becomes visible. They stream outward in numbers almost unimaginable, trillions upon trillions racing across space at nearly the speed of light. For a brief instant, the universe is filled with a silent storm of ghostly particles, each carrying a message from the heart of a dying star. When the supernova in the Large Magellanic Cloud erupted in 1987, detectors on Earth recorded this neutrino burst before the explosion's light appeared in the sky, a subtle whisper from the core reaching us faster than the brilliant flash that followed. The shock wave of a supernova travels outward with immense power, sweeping up gas, dust, and cosmic debris in its path. As it expands, it carves a shell into the interstellar medium, pushing it into intricate shapes and glowing filaments. These shock waves can travel for thousands of light years, compressing clouds of gas ahead of them and triggering new waves of star formation. In this way, a single death can lead to the birth of many new stars, each ignited by the pressure of the shock front moving through space. Over thousands of years, the remains of the explosion cool and drift, forming colorful nebula that stretch across light years, evidence of a star's existence long after its light has faded. These remnants glow with the faint but persistent energy left behind, intricate threads of material sculpted by the force of the explosion. Standing back to consider the scale of a supernova, it becomes clear how enormous these events truly are. The energies released in a single explosion exceed what our sun will produce in its entire 10 billion year life. The blast sends matter into space at speeds unimaginable to the human mind, creating structures that span light-year distances. And yet, these explosions are common across the universe. They happen quietly and invisibly to us, their light sometimes too faint or too distant to be noticed without telescopes. While you sleep, somewhere in a distant galaxy, a star is collapsing, releasing its final light into the vastness. What makes supernovae so significant is not just their size or energy, but what they leave behind. They shape the chemical composition of galaxies. They forge the elements that make planets and life possible. They create neutron stars, dense, spinning cores that pack a sun's mass into a sphere the size of a city, or black holes, where gravity becomes so strong that not even light can escape. The universe you know would not exist without supernovae. Every atom heavier than hydrogen or helium has passed through the furnace of a dying star. And so, in the quiet of night, when a faint star twinkles above you, it's possible that you're seeing the descendant of a long-vanished predecessor, a light born from the ashes of a supernova that once glowed brighter than any galaxy. These explosions are both the universe's most violent moments and its most creative. They remind you that endings and beginnings are woven together, and that even in destruction, there is a kind of beauty, an immense, radiant release that reshapes the cosmos and scatters the ingredients of new life into the dark. Neutron stars begin in chaos, forged from the collapsed core of a massive star that has just torn itself apart in a supernova. What remains is a remnant so dense, so compact, that almost every familiar idea about matter breaks down inside it. Imagine taking a mountain, or a city, or even something as vast as the Himalayas, and compressing it until it fits into a sphere barely 20 kilometers across. That is the scale of a neutron star. The entire mass of the sun squeezed into something the size of a small town. Its density is beyond comprehension. A single teaspoon of neutron star material would weigh billions of tons, more than mountains, more than oceans, more than anything the human mind has ever lifted or imagined lifting. Inside this star, matter is crushed into a state where protons and electrons have fused into neutrons, packed so tightly they resemble an ocean of nuclear particles, all pressed together in an impossible stillness. This density makes neutron stars some of the strangest objects in the universe. They are heavier than white dwarfs, but not quite massive enough to collapse into black holes. Instead, they exist in a unique domain where the forces that govern nuclear physics take over, balancing gravity's pull with the pressure of neutrons resisting being squeezed into nothingness. The surface of a neutron star is not like any surface on Earth. If you could stand on it, which you cannot, the ground beneath you would be so hard it makes diamond look soft. The crust is a lattice of atomic nuclei, frozen in a pattern so dense and stiff that it could be considered the strongest material in existence. And yet, beneath that crust lies a sea of degenerate matter, a place where individual atoms no longer exist, and where neutrons drift in a superfluid, a frictionless quantum liquid that moves without resistance. It is a realm nature does not create anywhere else. Among neutron stars, some are even more extreme, magnetars. These are neutron stars with magnetic fields so strong they defy the imagination. Earth's magnetic field is gentle, almost delicate, guiding compasses and shaping auroras. A magnetar's magnetic field is 1 trillion times stronger, capable of warping atomic structures and tearing matter apart. If a magnetar were as close as the moon, its magnetic field could erase every credit card on Earth and scramble electronics across the planet. Near its surface, physics behaves differently, as if the rules have bent under the weight of the field. Light itself can be altered, split, or polarized by the magnetic tension, and the space surrounding the magnetar becomes a kind of quantum storm that few instruments can properly interpret. These fields decay over time, but while they last, they are the most powerful magnetic forces known in the universe. Neutron stars also spin with incredible speed. Some rotate so quickly they complete dozens or even hundreds of revolutions every second. These are pulsars, neutron stars that emit beams of radiation from their magnetic poles. As they spin, these beams sweep across space like the beams of a lighthouse, creating rhythmic pulses of light that reach Earth with astonishing regularity. The fastest pulsars spin hundreds of times per second, faster than the blades of a jet engine, faster than anything mechanical humans have ever built. This speed is not constant. Over time, pulsars gradually slow down as they radiate energy into space. But even in their decline, they maintain a precision that rivals or exceeds atomic clocks. Their pulses help astronomers measure vast cosmic distances, detect gravitational waves, and map the structure of the Milky Way with exquisite accuracy. Each spin is a reminder of the enormous forces that set these stars into motion long ago. Beneath the spinning crust lies a layer so thin and so strong, it becomes one of the most surprising features of a neutron star. The crust, only about a kilometer thick in most cases, must support the incredible weight of everything above it. It is made of nuclei in patterns we rarely see in nature. Long rods, flat sheets, and even strange shapes dubbed nuclear pasta, each more rigid than anything familiar. These formations result from the intense pressure and density, causing matter to arrange itself in unusual, almost crystalline structures. This crust is so strong it can hold mountains, tiny ones, no taller than a few centimeters, that still weigh as much as a small asteroid. When the crust cracks, the starquakes that result can release more energy than any earthquake recorded on Earth. These quakes can even shift the rotation rate of the star, causing sudden jumps in its timing that ripple outward through the signals astronomers detect. The gravity at the surface of a neutron star is overwhelming. If you dropped a pebble from a height of 1 meter, it would strike the surface at nearly the speed of light, releasing enormous energy from even the smallest fall. A human standing there, if such a thing were possible, would be crushed instantly under the weight of trillions of tons of force. Even light struggles to escape, bending noticeably as it climbs away from the surface. The curvature of space becomes pronounced, warping paths and stretching time. General relativity, a set of rules that normally feels abstract and distant, becomes intensely relevant here. Moments tick differently near the surface, and distances behave in ways the human mind is not accustomed to imagining. Gravity holds everything together with relentless strength, and yet, despite this unimaginable pressure, the neutron star does not collapse further. Something deeper inside resists. The neutrons, crowded together in the core, generate enough pressure to keep gravity at bay. This delicate balance defines the very existence of neutron stars. Push them slightly beyond their mass limit, and their structure fails. Gravity overwhelms every resistance, and the star collapses into a black hole. But within the mass range they occupy, neutron stars remain one of the universe's greatest paradoxes. Incredibly heavy, yet incredibly small, impossibly dense, yet impossibly stable. Their extremes create environments where matter behaves like liquid and solid simultaneously, where magnetic fields can tear space, where time itself bends differently from one moment to the next. In the quiet of space, these stars spin and glow, remnants of once luminous giants now compressed into cosmic embers. Their pulses drift across the galaxy, carrying stories of ancient explosions and gravitational dances lost to time. A neutron star, from afar, looks calm and still, but within it lies a storm of physics pushed to its limits. They are reminders that even in the universe's smallest survivors, vast forces are at play, forces that shape galaxies, seed star systems, and whisper across the cosmos long after the explosion that gave them birth has faded into memory. Black holes begin with collapse, a star so massive that nothing can to stop its inward fall once its nuclear fuel is gone. The core contracts under its own gravity, shrinking smaller and smaller until it reaches a point where the very idea of size becomes slippery. This threshold is marked by what physicists call the Schwarzschild radius, the distance from the center at which escape becomes impossible. For a black hole with the mass of the Sun, this radius would be just 3 kilometers. For something as heavy as the Earth, it would be no bigger than a marble. Yet within that boundary, gravity becomes overwhelming. Light, which normally races freely across the universe, cannot rise from the well that forms. Space curves inward, time stretches. The region inside becomes cut off from the rest of reality, a place sealed behind an event horizon where the rules of physics bend in ways that challenge understanding. Approaching a black hole is an experience no traveler could witness and survive, but imagining it reveals the scale of the forces at play. As you drift closer, tidal forces begin to take hold. Gravity does not pull uniformly. The difference in attraction between your head and your feet grows extreme, stretching your body in one direction while compressing it in another. This effect is sometimes described with a name meant to evoke both wonder and terror: spaghettification. Near small black holes, these tidal forces become lethal long before you reach the horizon. Near larger black holes, the gradient is gentler at first, luring you inward with a deceptive calm. But the closer you fall, the more dramatic the stretching becomes. Your sense of direction falters. The very geometry of space distorts. The familiar three-dimensional order begins to feel unstable, as if space itself is being pulled into a funnel. At the heart of every black hole lies something even stranger. The singularity is the ultimate breakdown of the known laws of physics, a point where density becomes infinite and space-time curves so sharply that our equations fail. We have no language adequate to describe it. It may not be a point at all, but a region where quantum effects dominate in ways we cannot yet grasp. Time and distance lose their meaning. Some theories suggest the singularity might not even exist in the form we imagine. Instead, the collapsing matter might smear into a ring or a shell, or perhaps evaporate into a quantum foam. Others propose that what we call a singularity may be a doorway to something else, another region of space-time, or a branching universe beyond our own. But from the outside, none of this can be confirmed. The event horizon hides everything within, allowing no message, no particle, no clue to escape. Outside that horizon, however, black holes are anything but silent. Surrounding many of them are accretion disks, vast spirals of gas, dust, and shattered stars drawn inward by gravity. As this material orbits faster and faster, friction and magnetic turbulence heat it to extraordinary temperatures, causing it to glow with intense light. Some disks blaze so brightly they outshine entire galaxies, announcing the presence of a black hole across unimaginable distances. Jets of charged particles may erupt from the poles, powered by twisted magnetic fields and the rotation of the black hole itself. These jets can shoot out for thousands of light years, marking the black hole like cosmic beacons. From afar, a black hole is not darkness but brilliance, a lighthouse powered by gravity's most extreme engine. Yet the most subtle and haunting effect near a black hole is time dilation. Time does not tick evenly throughout the universe. Gravity slows the passage of seconds, stretching them thin as one approaches the event horizon. If you watch someone falling toward a black hole, their movements would slow until they appeared frozen at the edge, their light redshifting into deeper and deeper wavelengths. From your perspective, they would never cross the horizon. From their perspective, They would plunge inward in moments, entering a realm they could never describe. Time's flow becomes fractured, uneven, almost fluid. The deeper the gravitational well, the more stretched time becomes, until it nearly stops at the horizon. A strong enough telescope aimed at someone falling could watch their last moment play out forever, suspended in a cosmic pause. This isn't just theoretical. Astronomers have observed the effects of time dilation around black holes through the shifting frequencies of light emitted from orbiting gas. They see time slow in the glow of the accretion disk. They measure the warping of orbits. And in the center of our own galaxy, they have watched stars whip around a hidden point, a gravitational anchor, tens of thousands of times heavier than the Sun, marking the location of Sagittarius A*, the supermassive black hole that holds the Milky Way together. It is quiet now, but evidence shows it once flared far more brightly, feeding greedily on gas drawn inward. Now, it sits mostly dormant, a stillness that hides immense potential. Even though nothing can escape a black hole, they are not permanent prisons. According to theoretical physics, black holes may slowly evaporate through a process known as Hawking radiation, releasing particles over eons until they vanish entirely. For small black holes, this evaporation would accelerate dramatically near the end, releasing bursts of energy. For supermassive ones, the process is so slow it lies far beyond the current age of the universe. Still, the idea that something so immense and so consuming could eventually fade into nothingness adds another layer of mystery to their nature. Black holes challenge every intuition humans have about the world. They compress mass into impossibly small spaces. They warp time like clay. They create regions where causality and geometry blur. And yet, far from being rare aberrations, they are woven into the structure of galaxies, shaping star formation, anchoring spiral arms, and locking entire stellar systems into place. They are part of the universe's life cycle, born from dying stars, sculpting their surroundings, and returning their energy across unimaginable stretches of time. To think of a black hole is to confront the limits of human comprehension. They are reminders that the cosmos is not always gentle or understandable. Some corners of space operate under pressures and forces so immense they rewrite the rules that govern everything else. Yet within that darkness lies a kind of beauty, a stark, quiet, relentless truth about nature's extremes. Black holes are not just destroyers, they are keepers of secrets, pillars of galaxies, and doorways to physics we have not yet discovered. And somewhere out there, far beyond the dim light of familiar stars, more of them are waiting, silent and ancient, shaping the universe from behind horizons we can never cross. Star systems are not always solitary. Though our sun wanders the galaxy alone, many stars are born in pairs or groups, sharing their early lives in webs of gravitational connection. These systems form inside clouds of gas that collapse under their own weight, and as the material fragments, multiple stars can ignite side by side. What seems calm from afar is, in fact, a subtle dance of mass and motion. The distances between stars in a binary system can vary enormously. Some pairs orbit so closely that their surfaces brush against each other, transferring heat and gas across a narrow bridge. Others live far apart, separated by hundreds or thousands of astronomical units, bound only by the faint pull of gravity across the cold reaches of space. For the stars themselves, these distances define their relationship, sometimes peaceful, sometimes turbulent, always shaped by the rhythm of their orbits. In close binary systems, stars may interact so intensely that they change each other's evolution. A giant star might swell in its old age, spilling its outer layers onto its companion like water overflowing from a basin. The smaller star, suddenly fed by a flood of new fuel, may burn hotter and brighter as its partner withers. Astronomers observe these relationships with fascination, watching how gravity binds two suns into a shared destiny. Their story is written in spirals of gas and shifts in brightness, a narrative revealed through delicate variations of light. These systems remind us that stars are not static spheres, but dynamic, living entities influenced by the companions that orbit alongside them. Beyond simple binaries lie multi-star systems, where 3, 4, or even more stars share one gravitational family. In these systems, the orbits grow intricate. One pair might revolve tightly around each other, while a third circles from afar, forming a hierarchy that allows stability even in apparent chaos. Some stars weave complex braids of motion, passing near one another in long, looping paths that repeat over centuries. Others maintain wide, slow cycles, drifting so gently that an entire human history could unfold between one approach and the next. Despite the complexity, these systems persist because gravity organizes them with quiet precision. The rules that keep them stable echo the same physics that shape galaxies and planetary systems, reminding us that order can arise even where the patterns appear tangled. The stability of planets within these systems depends heavily on the distances and motions of their suns. A planet orbiting a single star feels a predictable pull, a rhythm that rarely changes. But a planet in a binary system must navigate a more delicate path. If it orbits both stars, a circumbinary planet, it must remain far enough away to avoid the shifting gravitational tides created as the stars dance around each other. If it orbits only one star, then the companion must remain sufficiently distant that its influence does not disrupt the planet's delicate equilibrium. These subtle balances determine whether a world can remain intact for billions of years or whether it will be ejected, shattered, or swallowed by a drifting star. And yet, despite these challenges, planets in multi-star systems have been discovered across the galaxy, proving that life's raw ingredients may orbit under the glow of more than one sun. Consider wide binaries, where stars are separated by distances so vast they seem to drift alone. These pairs may lie thousands of astronomical units apart, linked only by the faintest threads of gravitational pull. Over millions of years, passing stars or clouds of gas might tug at them, stretching their orbits or even pulling them apart entirely. But until those encounters occur, the stars remain bound in a long and silent partnership, tracing enormous loops around a center of mass that lies somewhere in the thin space between them. These systems challenge our intuitions about what it means to be connected, even when separated by distances greater than those between planets and their suns. The stars still feel each other's presence, their trajectories forever shaped by that faint, mutual attraction. In closer systems, the dance becomes more dramatic. As two stars orbit, their motion can create a shifting tapestry of light, especially if their orbits are inclined in just the right way from our point of view. One star may pass in front of the other, dimming the combined glow in a pattern so regular it becomes a cosmic heartbeat. These eclipsing binaries allow astronomers to measure stellar sizes and masses with extraordinary precision, enabling insights into how stars age and how they exchange energy. Each dimming event is like a whisper of information, delivering clues about the hidden architecture of the system. Even when we cannot see the individual stars clearly, their synchronized flickers reveal the secrets of their shared orbit. Some star systems contain pairs so tightly bound they spin around each, other in hours rather than days or years. In such systems, centrifugal forces distort their shapes, stretching them into elongated forms that bulge at the equator. Their shared gravity shapes them into a teardrop-like configuration, with each star's outer layers almost brushing against the other. These extreme binaries create powerful streams of material that arc through space like glowing waterfalls, transferring hot plasma from one star to another. Over time, this exchange can drastically alter their fates, accelerating one star's evolution while stripping another down to its core. In the night sky, they appear as single dots of light, but behind that simplicity lies a history of intimate and constant interaction. Even more elaborate are systems where stars rotate in nested orbits, each circle influencing the others. Imagine one pair spinning tightly in the center, while another star loops around them from afar, and perhaps even a fourth star winding in an even larger orbit. These systems can produce long-term oscillations in their dynamics, shifting the inner star's orbits and occasionally triggering dramatic changes like mass transfer or orbital collapse. Over centuries and millennia, their patterns drift like the slowly shifting gears of a cosmic machine, each part influencing the others with subtle but profound force. These interactions reveal the flexibility of gravity, how it adapts to the presence of multiple bodies and orchestrates their motion into stable rhythms. For astronomers watching from across the galaxy, binary and multi-star systems are like distant dances. Their movements, though slow on human timescales, tell stories of balance, tension, and deep interconnection. When the light from these systems reaches Earth, it carries whispers of those dances, flickers of brightness, shifts in color, slight variations in timing. Each change encodes a moment in the star's shared journey, a reminder that even distant suns feel the pull of each other's gravity. In a universe filled with isolated stars, these systems stand out as a testament to the quiet relationships formed by mass and motion. They show us that the cosmos is not simply a scattering of lone lights, but a place where companionship, however strange and distant, can endure for billions of years. And as the galaxy turns, these stars continue their steady choreography, bound together by the same forces that hold planets in orbit and shape the paths of galaxies themselves. Their dances may be slow, but they are eternal, unfolding across epochs in the silent space between worlds. Nebulae are some of the most delicate structures in the universe, yet they stretch across distances so vast that human imagination strains to hold them. A single nebula can span dozens or even hundreds of light years, its boundaries drifting softly through the interstellar medium like smoke from a distant fire. These clouds are not solid objects, but diffuse gatherings of gas and dust, their shapes carved by gravity, radiation, and the movement of stars. Most of the material inside them is thinner than the best vacuum humans can create. But the clouds are so enormous that even this sparse gas becomes visible when starlight illuminates it. In the vastness of a nebula, the emptiness is part of the beauty. It allows light to filter through in gradients, forming soft glows and faint shadows that give each nebula its haunting, dreamlike appearance. From afar, they resemble cosmic watercolor paintings, their edges fading into darkness like breath dissolving into cold air. These birthplaces of stars begin as cold, dark clouds. Deep inside their shadows, the gas is dense enough for gravity to gain a foothold, slowly pulling atoms together across spans of millions of years. As pockets of gas collapse, they grow warmer, forming knots of matter that will eventually ignite into newborn stars. These regions are often hidden behind veils of dust, invisible to the naked eye, but infrared telescopes reveal what lies inside: pillars, ripples, and tangled threads shaped by invisible forces. Some regions look calm and smooth, but others are stormy, filled with turbulent waves of gas that churn under the pressure of nearby stars. Each cloud holds countless futures within it, some destined to burn brightly for billions of years, others to remain dark and quiet as failed stars or drifting dust. The density of gas within these clouds is astonishingly subtle. Imagine a room filled with air. Now imagine spreading that air out across a space larger than the solar system, thinning it until only a few atoms remain in each cubic centimeter. That is the density of many nebulae. And yet, because these clouds extend for such enormous distances, their mass accumulates, forming a reservoir of raw material from which stars are born. In the coldest regions, molecules of hydrogen cling together, forming the simplest and most abundant building blocks of the cosmos. These molecules drift silently, occasionally colliding, letting gravity sort them into flows and filaments. Over time, the densest regions shine in radio wavelengths, revealing cold knots where the seeds of future suns are gathering in slow, patient spirals. When young stars finally ignite within a nebula, they release intense radiation that pushes outward in every direction. The edges of the surrounding cloud respond with brilliant displays called ionization fronts, where ultraviolet light strips electrons from gas molecules and causes the cloud to glow. These glowing edges often form towering pillars, sharp ridges, or soft arcs, their shapes sculpted by the new star's fierce winds. The most famous of these features, the pillars of creation, rise like ancient monuments, each one shaped by radiation from nearby stars blasting away the surrounding gas. These ionization fronts mark the boundaries between darkness and light, between quiet, cold, and radiant heat. Their motion is slow on human timescales, but over millions of years, they drift, evaporate, and reshape the nebula around them. The stars that created them continue to burn nearby, unaware of the structures they carve with their light. Color in nebulae comes from the interaction of light with gas. Hydrogen often glows deep red when ionized, while oxygen can shine blue-green, giving some nebulae their ethereal hues. These colors are not simply artistic interpretations. They reflect real chemical processes happening across enormous expanses of space. In many nebulae, different regions shine with different colors depending on their temperatures, densities, and the types of stars that illuminate them. Some areas glow with warm reds and oranges, others with cool blues and purples. Dust absorbs and scatters starlight, creating pockets of darkness that resemble ink spots against luminous backgrounds. Through telescopes, these colors become maps guides to the physics unfolding within them, and they reveal how the stars shape the very medium from which they were born. Birth clouds are not quiet places. The moment a star forms, it begins to alter everything around it. Its radiation heats nearby gas, causing it to expand and drift away. Winds from the star push outwards, blowing bubbles into the surrounding cloud. In some regions, clusters of young stars form together, their combined energy carving enormous cavities that can stretch across dozens of light years. These hollowed spaces become the backdrop for future star formation, as shock waves move through the clouds, squeezing gas into new knots that collapse into the next generation of stars. Nebulae are not static images. They are living, changing environments where the cycle of creation and destruction plays out in slow, graceful motions. The scale of these places is almost impossible to grasp. A single light year, about 9 trillion kilometers, serves as a unit of measurement in nebulae, the way centimeters serve for everyday objects. When astronomers describe a cloud as being 50 light years across, they are describing a structure so vast that even the fastest spacecraft would take tens of thousands of years to cross it. And yet, from a distance, these clouds appear delicate, as if a breeze could shift their shapes. This illusion of fragility is part of their allure. A nebula can look like a thin wisp drifting through the void, but in truth it is a colossal structure containing enough material to form thousands of stars. Inside these clouds, young stars are sometimes still wrapped in cocoons of dust. These protostars flicker faintly, their light struggling to escape the thick layers around them. As they grow brighter, their heat evaporates the dust, slowly peeling back the layers until the star emerges fully into the surrounding nebula. This moment marks the beginning of a star's independent life. The dust and gas around the new star may flatten into a disk, forming planets, moons, and comets that will orbit it for eons. All of it begins in the quiet darkness of a nebula, where atoms drift until gravity pulls them together into something that can burn. As the years pass, the nebula changes shape. Ionization fronts push outward, new stars ignite, and old ones drift away. Eventually, the cloud dissipates, leaving behind a cluster of young stars shining against the blackness. The nebula that gave them life fades, becoming part of the interstellar medium once again. But the stars remain, living out their long lives as reminders of the cloud that shaped them. Nebulae, in their vast beauty, remind us that even the largest and most radiant objects in the universe begin in darkness. They are cradles of creation, woven from the thinnest threads of gas and dust, yet capable of giving rise to suns, planets, and the conditions for life itself. In their colors and shapes, they hold the quiet story of how the cosmos renews itself, again and again, across the endless night. The solar system seems familiar at first glance, a handful of planets circling one golden star. But when you begin to measure it, truly measure it, everything stretches far beyond the limits of easy imagination. The orbits, which look like tidy loops in textbooks, are actually vast ellipses sweeping through emptiness. Earth's orbit alone is nearly 300 million kilometers in circumference, a path we glide through without ever feeling the motion. Jupiter's orbit expands this scale dramatically, carrying the giant planet so far from the sun that sunlight reaching it has already dimmed to a soft glow. Farther still, Neptune completes a single revolution in the time it takes entire human civilizations to rise and fall. The distances between these worlds dwarf the planets themselves. The space between Mars and Jupiter, a silent gulf dotted with drifting rocks, is so wide it could contain thousands of Earths. To walk the solar system is to wander through a desert of distances where the grains of sand, planets float tiny and bright in a sea of black. Beyond Neptune lies the Kuiper Belt, a region filled with icy remnants from the dawn of the solar system. These objects, frozen and quiet, have orbited the sun for billions of years, barely disturbed by anything except the gentle tug of gravity. They range from small shards of rock to bodies nearly as large as planets, like Pluto and Eris, drifting in slow arcs far from the sun's warmth. Out there, sunlight grows weak and pale, its heat diluted until it offers little more than a whisper of warmth. The Kuiper Belt stretches for dozens of astronomical units, a glittering ring of debris that circles the sun like a fragile halo, too dim to see with the naked eye, but rich with the history of how our world began. Even farther out lies something more mysterious, the Oort cloud. Unlike the Kuiper Belt, which is a flat disk, the Oort cloud is a spherical shell surrounding the entire solar system, extending so far that the sun's light becomes no more than a bright star. The objects here, if they exist as astronomers predict, float loosely in a region that marks the boundary between our solar system and the interstellar void. Some of these icy bodies may be nudged inward by passing stars or faint gravitational tides from the galaxy itself, becoming the long-period comets that sweep through the inner solar system every few thousand years. The scale of the Oort cloud is almost beyond comprehension. Its outer edges may lie a light year from the sun, meaning that the solar system's true size is not the span of the planets, but a sphere vast enough to hold trillions of comets drifting in near-frozen silence. All of this exists within the heliosphere, a bubble carved into the galaxy by the solar wind. This wind is not a breeze, but a stream of charged particles released by the sun's corona, flowing outward at hundreds of kilometers per second. As these particles travel into space, they push against the interstellar medium, shaping a protective bubble around the solar system. Within this region, the sun's influence dominates. Its radiation, magnetic field, and particle streams define the environment through which planets move. At the edge of the heliosphere, this solar wind slows, interacts with the thinner material between stars, and forms a boundary called the heliopause. Beyond that frontier lies interstellar space, a realm where the sun's voice grows faint and other stars begin to assert their influence. Voyager 1 and Voyager 2, tiny emissaries launched decades ago, have now crossed this boundary, carrying with them a message from Earth and drifting through the cold dark between the stars. The solar system is often imagined as a tight cluster, but in truth, it is a sparse network held together by one overwhelming force, the sun's gravity. Though more than 99% of all mass in the solar system resides in the sun, Its reach extends far beyond the orbit of Neptune. Even at the distance of the Oort cloud, its tug remains just strong enough to keep icy bodies loosely bound. The solar influence stretches across trillions of kilometers, shaping the motion of objects that will never be warmed by its light. This subtle pull is the glue that gives the solar system its form. Without it, the planets, asteroids, comets, and dust would drift away into the galaxy, becoming wanderers lost among the stars. Closer to home, the sun's influence is more immediate. It drives the chemistry of atmospheres, powers, weather systems, and fuels life on Earth through its radiant energy. Its flares and storms ripple through the solar system, stirring magnetic fields and pushing waves of particles outward. These particles can disrupt spacecraft, ripple auroras across planets with magnetic fields, and shape the long tails of comets as they sweep close to the sun. Even the most distant planets feel this influence faintly, their atmospheres stirred by the pressure of the solar wind. Across billions of years, the sun has been both a source of warmth and a sculptor of worlds, shaping the solar system with steady, radiant force. The comparative orbits of the planets reveal patterns that feel almost poetic. Mercury, racing closest to the sun, completes 4 years in the time Earth completes 1. Venus orbits more slowly, a smooth and gentle path wrapped in clouds. Mars wanders outward into colder regions, where sunlight weakens and shadows deepen. The gas giants, each enormous and swirling with storms, drift in slow, majestic arcs, their orbits so wide that they enclose entire realms of smaller, icy bodies. Pluto's orbit crosses Neptune's in a delicate exchange that repeats over centuries, a reminder that even in cosmic mechanics, there is a kind of choreography. When you consider these distances and motions together, the solar system reveals itself as a vast, dynamic structure, a place where emptiness is the dominant landscape, where planets are islands separated by unimaginable expanses. And yet, despite its scale, everything is connected by the sun's gravity and illuminated by its light. The solar system breathes through the heliosphere, drifts through the galaxy as a single unit, and carries with it the records of its own formation in the icy bodies that linger on its edges. In the quiet of night, when you look up at the sky, you see only the faintest hint of this immensity. The planets appear as points of light, but beneath that simplicity lies a structure so large and so delicately balanced that even 1,000,000 lifetimes would not be enough to traverse its boundaries. The solar system is not small, and it is not simple. It is a cathedral of motion, distance, and silence, stretching outward from one bright star into a darkness that has no end. Distances between stars are so immense that ordinary units break down under the weight of their scale. Kilometers become meaningless, astronomical units too small, and even the span of entire planetary systems begins to feel tiny. Instead, the universe stretches itself across light years, a measure born from the speed of light, the fastest thing we know. 1 light year is nearly 10 trillion kilometers, a distance no human has ever traveled, nor ever truly felt. When we say the nearest star, Proxima Centauri, is just over 4 light years away, it sounds close until you imagine light itself needing 4 years to cross that gulf. A spacecraft traveling at the fastest speed humanity has ever achieved would take tens of thousands of years to reach it, drifting through a darkness so deep and unbroken that time begins to feel like a physical substance. In this quiet, the very concept of near becomes almost poetic, a reminder of how small our neighborhood is in the grand expanse of the galaxy. Astronomers use parsecs to map these distances more precisely, a unit tied not to speed but to geometry. 1 parsec is a little over 3 light years, born from the way a star appears to shift ever so slightly in the sky as Earth moves around the sun. This shift parallax is so subtle that even the closest stars move only fractions of an arcsecond. Yet from these tiny angles, astronomers have built a 3-dimensional map of the galaxy. each star plotted by the faint waver of its position. A parsec is not just a unit, it is a method, a way of measuring depth in the universe using the smallest of motions. When astronomers say a star lies 10 or 50 or 100 parsecs away, they are describing positions carved out of nearly imperceptible movements, like reading the shape of a vast room by watching shadows drift across a wall. Our nearest neighbors in space form a small, loosely knit family that drifts through the galaxy alongside the Sun. Besides Proxima Centauri, Alpha Centauri, A and B lie close together, forming a triple star system about 4.37 light-years away. Beyond them are Barnard's star, Wolf 359, Sirius, Epsilon Eridani, each a point of light in the sky, yet vast, blazing worlds unto themselves. Some are dim, red dwarfs, burning quietly, nearly invisible to the naked eye. Others shine brightly, filling their regions of space with intense radiation. Yet in every case, the distances between them remain staggering. The Sun's nearest neighbors are not like houses on a street or towns across a countryside. They are solitary campfires glowing across a frozen wilderness, each separated from the next by expanses so wide that entire planetary systems drift through them unnoticed. Stars do not stay fixed in place. They move through the galaxy like swimmers in a slow cosmic current. This motion, called stellar drift, reshapes the night sky over millions of years. Constellations that look permanent, Orion, Ursa Major, Cassiopeia, are merely temporary arrangements, patterns formed by chance alignments of stars that are each following their own paths. Some stars move quickly across the sky relative to the Sun, their proper motions, revealing them as wandering neighbors. Barnard's star, for example, glides more rapidly than most, shifting its place year after year. Others drift so slowly that their motion is almost invisible on human timescales. Over millions of years, stars approach and recede from one another, passing like ships in a boundless ocean. Occasionally, one will drift close enough to disturb the outer regions of another system, nudging comets, stirring dust. But most continue on their long journeys, undisturbed, each carrying the memory of its birthplace as it migrates through the galactic disk. The space between stars is not empty in the way a vacuum chamber is empty. It is emptier than that by unimaginable degrees. If you placed a cubic meter of interstellar space beside you, it might contain a few stray atoms, hydrogen, mostly floating alone in a vast void. The emptiness is so profound that it challenges the mind. Light travels through this darkness without resistance. Comets drift for ages without colliding with anything. A grain of dust can travel for centuries before meeting another grain. Even dust clouds that span light years are mostly empty, their beauty revealed only when illuminated by starlight or captured in long exposures. This emptiness is the canvas on which the galaxy paints its structures. Without it, stars would crash together, planets could not orbit safely, and nebulae would collapse too quickly to give birth to new suns. Yet this empty space is not truly silent. It hums faintly with cosmic rays launched from distant explosions. It carries the cold whisper of the cosmic microwave background, the afterglow of the Big Bang. Magnetic fields thread through it like invisible wires. Thin tendrils of gas drift in long, slow currents, shaped by the motion of stars and the pull of gravity. To cross the space between stars is to wander through a realm that feels both impossibly desolate and strangely alive, filled with energies and particles born in places far beyond sight. When you gaze at the night sky, every star you see is separated from every other by these unfathomable distances. The light that reaches your eyes has traveled for years or centuries across space, crossing voids where no worlds shine and no suns warm the dark. And yet, from Earth, the stars seem close. They shimmer together as if scattered across a single dome. That illusion is comforting, a reminder that from our perspective, separated by only a thin atmosphere, the universe can feel intimate. But behind that closeness lies a truth more enormous than anything we encounter in daily life. The distances between stars define the shape of the galaxy. They allow planets to orbit in peace, nebulae to evolve, and entire civilizations, if they exist, to rise without being burned or torn apart by nearby suns. Space must be large for life to flourish. It must be quiet and wide and slow. The stars drift through it like lanterns carried across a nighttime field, each one keeping its distance, each one following its path, creating a cosmos where silence is not emptiness, but a necessary space for everything to be. And so the vastness between stars, instead of being a void, becomes a kind of gentle distance, a cosmic breath that gives the universe room to form, to grow, and to shine. The Milky Way is more than the soft band of light we see stretching across the sky on clear nights. It is a vast and intricate structure, a rotating island of stars, gas, and dark matter that spans 100,000 light-years from edge to edge. When you look at it from within, the glow seems gentle, like a faint river of starlight. But if you could rise above it and see it from a great distance, the galaxy would unfurl into a sweeping spiral, its arms curling outward in graceful arcs. These spiral arms are not solid structures, but waves of density regions, where stars and gas gather more closely, creating patterns that drift slowly as the galaxy turns. Inside the arms, new stars ignite from clouds of gas, their young blue light shining brightly before they drift into the quieter regions between the arms. The arms themselves move more slowly than the stars within them, allowing stars to pass through as if entering and exiting a celestial traffic jam that has lasted for billions of years. At the center of the Milky Way lies a bar-shaped structure of tightly packed stars. This bar stretches nearly 27,000 light-years from end to end, funneling gas toward the galactic core and helping to drive the spiral arms outward. The bar does not rotate at the same speed as the rest of the galaxy. It moves as a kind of inner engine, shaping the motion of stars throughout the disk. Embedded within this bar is Sagittarius A*, the supermassive black hole around which the entire galaxy orbits. Though this black hole is quiet now, barely feeding on surrounding material, its gravitational pull anchors the Milky Way, keeping the inner regions bound in a dense, swirling cluster. The stars in this central region move so quickly that their orbits resemble spinning sparks, each darting through a crowded field of light with speeds that dwarf anything found near our sun. Beyond the visible disk lies the galactic halo, a vast and diffuse sphere of stars, ancient clusters, and dark matter that extends far beyond the spiral arms. The halo reaches out for hundreds of thousands of light years, enveloping the Milky Way in a ghostly shell. Most of the halo is almost entirely empty, with stars scattered so thinly that an entire cubic light-year might hold only a single one. Yet the halo is massive, its dark matter shaping the galaxy's structure and governing the speed of its rotation. Without the halo's gravitational presence, the spiral arms would not hold together. They would unravel over time, flinging stars outward into intergalactic space. The halo is the invisible skeleton of the Milky Way, a framework without which everything else would fall apart. The Milky Way contains hundreds of billions of stars, each with its own story, some small and faint, others enormous and blazing, many accompanied by planets drifting in long arcs around them. These stars are not evenly distributed. Some regions of the galaxy are densely packed, glowing with the combined light of millions of suns. Others are quiet and dark, islands of space where stars are few and far between. There are clusters that form together from the same cloud of gas, still tightly bound after billions of years, and others that have already drifted apart. There are lone stars wandering the galactic disk, bound only loosely to any group, and there are streams of stars stretched across space, remnants of ancient galaxies torn apart by the Milky Way's gravity and absorbed into its structure over cosmic time. All of these stars, clusters, and clouds move together in a grand rotation around the galactic center. The Sun itself orbits at a distance of about 26,000 light-years from Sagittarius A*, completing one full revolution roughly every 230 million years. This means that since the dinosaurs first walked the Earth, the solar system has completed only a single orbit of the galaxy. As the Sun travels, it bobs up and down slightly within the galactic disk, drifting through regions of varying density and passing near spiral arms in cycles that last hundreds of millions of years. The stars around it follow similar paths, though each carries its own velocity and slight deviations, creating a subtle shimmer of motion across the disk. On larger scales, the Milky Way itself is not stationary. It moves through the local group, pulled toward the Andromeda Galaxy, as the two spiral giants slowly approach one another. In about 4 billion years, they will merge in a long and graceful collision that will reshape both galaxies into a new, elliptical form. Even now, the Milky Way and Andromeda are drifting closer at hundreds of kilometers per second, while smaller nearby galaxies dance around them in complex orbits. The entire local group moves together toward a region of space called the Great Attractor, drawn by the combined gravitational pull of hundreds of galaxies clustered there. And even this enormous structure is itself moving as part of the larger cosmic web. When you think of the Milky Way, it's easy to imagine something static, a fixed pattern of stars glowing in the dark. But the galaxy is alive with motion. Spiral arms twist as density waves ripple through them. Stars orbit in vast curves that take eons to complete. Gas clouds drift, collide, and give birth to new generations of suns. Clusters fall into the disk from the halo. The central bar slowly turns, guiding gas inward, and the entire galaxy glides through space as part of a larger network of cosmic structures that stretch across the universe. Yet, despite all this movement, the Milky Way remains beautifully balanced. Gravity ties its components into a single, harmonious system. Light from billions of stars weaves together into the faint band we see overhead, a reminder that even in the vastness of space, structure emerges from subtle forces acting over immense timescales. To stand on Earth and look up at the Milky Way is to see only a narrow slice of a much grander whole. But behind that thin ribbon of starlight lies a masterpiece of cosmic architecture, a galaxy shaped by time, gravity, and the gentle interactions of countless suns drifting in an immense, shared dance. Megastructures in space are not built by hands or machines. They are shaped by gravity, time, and the quiet interactions of matter drifting through the universe. When astronomers speak of the largest formations in the cosmos, they describe structures so enormous they defy the scale of anything familiar spans, measured not in kilometers or even light years, but in hundreds of thousands, sometimes millions of them. These formations are not simple or uniform. They twist, stretch, cluster, and branch in patterns that resemble natural growth, as if the universe itself were weaving a tapestry from the faint threads of its own substance. Globular clusters are among the most striking of these structures. They hang like lanterns in the halos of galaxies, each one containing hundreds of thousands of ancient stars packed tightly into a sphere only a few dozen light-years across. The density at their cores is so extreme that stars lie far closer than anything found near our sun, their lights mingling until they form an almost continuous glow. These clusters are survivors, stellar fossils left over from the early days of galaxy formation. Their stars are old, nearly as old as the universe itself, and their orbits around the galactic center trace long, looping paths that can take hundreds of millions of years to complete. They drift through the outer regions of galaxies like glowing seeds carried by a cosmic tide, each one a reminder of how crowded and brilliant the young universe once was. Large nebula complexes, by contrast, are cradles of creation. They stretch across hundreds of light years, vast enough to hold thousands of star systems, yet delicate and translucent when seen from afar. Their clouds of gas and dust move in slow patterns, shaped by the birth and death of stars within them. Some regions are illuminated by massive young stars, whose ultraviolet light carves glowing cavities into the surrounding material. Others remain shadowed and cold, their dense cores collapsing quietly into new suns. These nebula complexes are not static. Over millions of years, winds from massive stars sculpt them into arches, pillars, and ripples, reshaping them into forms that resemble shifting landscapes. The Orion Molecular Cloud Complex, the Carina Nebula, the Rosette, each one is a continent of gas floating in interstellar space, its shape carved by invisible forces and glowing with the light of creation. Star streams are something more subtle. These long, faint ribbons of stars stretch across galaxies like trails of spilled light. They are the remnants of smaller galaxies or clusters that were torn apart by tidal forces as they passed too close to the gravitational pull of a larger galaxy. Over time, the stars from these disrupted systems spread out into long, graceful arcs that weave through the disk and halo. If you could see the Milky Way from above, some of these streams would appear like delicate strokes of paint winding around the main body of the galaxy. They reveal the Milky Way's history, showing where it has consumed or interacted with other systems. Each star stream carries the memory of a once cohesive group now stretched thin, but still identifiable by its shared motion and chemistry. These structures remind us that galaxies are not isolated, but constantly shaped by encounters with their neighbors. On even larger scales, galactic filaments span the universe like colossal strands in a cosmic web. These filaments form the framework of the large-scale structure of the cosmos, connecting clusters of galaxies across distances so enormous they dwarf the Milky Way. They stretch for hundreds of millions of light years, forming networks of matter that thread the universe together. Within them, galaxies gather like beads along a wire, drawn into alignment by the pull of gravity acting over eons. Between these filaments lie vast voids, regions of space with almost no matter at all. The result is a pattern that resembles a three-dimensional skeleton, a structure so immense that even the speed of light seems inadequate to describe its scale. These filaments are not visible to the eye, but they reveal themselves through the distribution of galaxies, the patterns of dark matter, and the faint glow of intergalactic gas. Molecular clouds, though far smaller than filaments, are still immense compared to anything found on Earth. These cold, dense regions of interstellar space can stretch for tens or even hundreds of light years, forming sprawling networks of gas where star formation unfolds slowly over millions of years. Their interiors are dark, shielded from starlight by thick layers of dust. In these shadows, molecules form hydrogen, carbon monoxide, more complex organic compounds, drifting through the cold, like silent, primordial fog. Some molecular clouds gather into enormous complexes, spanning hundreds of light years and containing enough material to form tens of thousands of stars. They are the nurseries of the galaxy, places where gravity and chemistry work together to create new suns and planetary systems. And yet, despite their size, these structures are fragile. A single massive star forming inside a molecular cloud can send out winds and radiation strong enough to erode entire regions of gas, creating cavities and tunnels that reshape the cloud's appearance. Over time, clusters of young stars hollow out bubbles that expand and merge, pushing gas outward until only thin shells remain. In this way, the largest molecular clouds are constantly changing, evolving as they feed the cycle of star birth. Megastructures of space are not isolated phenomena. They interact and blend into one another, forming layers of architecture that span from the small to the incomprehensibly large. A molecular cloud gives rise to a nebula complex. A nebula complex gives birth to star clusters. A star cluster drifts into the halo, eventually becoming part of a star stream. That stream wraps around the galaxy, which itself lies along a filament that stretches across the universe. Each structure is part of a larger one, nested like shells within shells. When you trace these connections, you begin to see the universe not as a random scattering of objects, but as a vast, interwoven system shaped by gravity, time, and the faint motions of matter drifting across unimaginable distances. The megastructures of space remind us that the cosmos is both intricate and immense, built from tiny particles that gather into clouds, clusters, and galaxies, until the entire universe becomes a tapestry woven from light, dust, and the silent pull of gravity. To contemplate these structures is to feel the scale of existence on a level words can barely reach a sense that the universe is both endlessly vast and beautifully ordered, stretching outward in patterns that have unfolded for billions of years and will continue long after our brief moment beneath its stars. Galaxies come in an astonishing range of sizes and shapes, each one a vast congregation of stars and dust woven together by gravity. Some are immense, sprawling across hundreds of thousands of light years, while others are so small and faint they could slip unnoticed between brighter neighbors. When you compare galaxies to one another, the differences reveal the incredible diversity of structures the universe has created. The smallest dwarf galaxies may contain only a few million stars, dim, clusters drifting quietly at the edges of larger systems, while the largest giants blaze with trillions of stars spread across grand spirals or enormous ellipsoids. These extremes coexist across the cosmos, shaping the environments where stars form, galaxies collide, and clusters assemble over billions of years. In every direction, galaxies carry their own histories, written in the arrangement of their stars and the faint halos surrounding them. Dwarf galaxies are some of the most common but least noticeable in the universe. Their light is faint, their structures fragile, and their stars widely spaced. Many orbit larger galaxies as quiet companions, their feeble gravity easily distorted by passing forces. Some dwarfs are irregular in shape, with tangled regions of star formation scattered unpredictably. Others are spheroidal, with older stars drifting in loose clouds that hang silently in the dark. Despite their small size, these galaxies play a crucial role in cosmic evolution. They are thought to be the building blocks of larger galaxies, merging over time to create grander systems. Many dwarfs that exist today are survivors of ancient eras, remnants that avoided absorption and now linger in the outskirts of major galaxies like the Milky Way. Their simplicity hides a deep history, one written in the slow movement of their stars and the quiet pull of unseen dark matter. At the other end of the scale are giant galaxies, structures so large and luminous that they dominate their regions of space. Some giants form elegant spirals, with long arms sweeping outward in patterns shaped by density waves and rotational balance. Others become enormous ellipticals, glowing spheres or elongated ovals formed through the mergers of many smaller systems. These ellipticals can stretch hundreds of thousands of light years, containing trillions of stars packed into a structure both massive and ancient. Their light is often warm and diffuse, filled with the glow of older stars. Little star formation takes place in these giants. Their gas has been consumed or heated by past collisions, leaving them to drift through space as immense, graceful relics of earlier, more turbulent eras. Elliptical galaxies vary widely in size, from small, faint spheroids to vast giants that dominate entire galaxy clusters. Their shapes come from the violent histories that created the mergers, collisions, and interactions that scrambled their original patterns. Instead of the orderly rotation found in spirals, the stars in ellipticals move in all directions at once, like bees inside a hive, their random orbits creating a smooth, rounded glow. These galaxies are often found in dense environments where interactions are common, and their sheer mass allows them to anchor clusters and impact the flow of matter across millions of light years. In the emptiness beyond their halos, Smaller galaxies continue to drift toward them over cosmic time, destined to merge and add to their already impressive bulk. Between spirals and ellipticals lies a transitional type known as lenticular galaxies. These systems have the flat, disc-like shape of a spiral but lack defined arms. Their stars orbit in orderly patterns, creating a structure that looks like a soft, smooth plate of light. Lenticular galaxies often form when spirals lose the gas they need to create new stars, leaving behind a disk of aging suns. They can result from interactions, from internal exhaustion, or from slow processes that strip gas away as the galaxy moves through dense regions of space. Lenticulars are quiet, stable systems, suspended between the chaotic birthplaces of spirals and the ancient calm of ellipticals. They are the middle-aged galaxies of the universe, still holding echoes of their younger forms but no longer lively with new creation. Some galaxies, though large in size, are surprisingly faint. These are the ultra-diffuse galaxies, ghostly systems so spread out that their stars are separated by enormous distances. A single ultra-diffuse galaxy might be as large as the Milky Way, yet contain only a fraction of its stars, making it appear almost transparent. They drift through galaxy clusters like pale shadows, their shapes faint and difficult to discern. The existence of these galaxies challenges assumptions about how galaxies form and what keeps them together. Their low densities suggest they should disperse, yet something, perhaps large amounts of dark matter, binds them in place. Some ultra-diffuse galaxies contain almost no dark matter at all, defying expectations entirely. They are enigmas on a colossal scale, silent anomalies that hint at complexities in the universe's structure that remain unsolved. The sizes of galaxies span an extraordinary range. Dwarfs may stretch only a few thousand light-years, barely visible even with powerful telescopes. Spirals like the Milky Way reach across 100,000 light-years, their arms sweeping outward in big, luminous arcs. Giants like IC 1101 extend nearly 6 times farther, glowing softly with the combined light of countless old stars. Even within similar types, the variation is enormous. Two galaxies that appear nearly identical in shape may differ in diameter by tens of thousands of light-years. These differences arise from their histories, how much gas they gathered, how many mergers they experienced, how their environments shaped them. Galaxy formation is not a single process, but a tapestry of interactions, collapses, and accretions unfolding across cosmic time. When comparing galaxies, their diversity becomes a testament to the universe's boundless creativity. No two are truly alike. Some are bright beacons of star formation, others ancient havens of aging light. Some drift alone in the quiet darkness between clusters, while others jostle in crowded environments filled with gravitational struggles. Their shapes, sizes, and brightnesses tell stories written over billions of years, shaped by forces vast and subtle. To study them is to glimpse the universe's grand design, one built from collisions, expansions, and the slow, graceful dance of matter under the influence of gravity. And through all of these differences, galaxies remain the fundamental structures of the cosmos, each one a home for countless stars, worlds, and possibilities. In their variety, they remind us that the universe is not monotonous but filled with wonders sculpted on scales far beyond human experience, drifting together in an endless sea of darkness and light. Intergalactic space stretches across distances so immense that even the idea of a galaxy, something already vast beyond easy comprehension, becomes small within it. Between galaxies, there are reaches of darkness where nothing shines, nothing stirs, and nothing marks the passing of time except the faint drift of radiation left over from the early universe. These spaces are far wider than the gaps between stars, while the nearest stars lie a few light-years from one another. Galaxies are separated by millions. To cross such a gulf would mean journeying through regions so empty that a single atom might be found in an entire cubic meter. And yet, These voids are an essential part of the universe's structure, the dark spaces that surround and define the brighter regions where galaxies gather. Voids themselves are not uniform. Some stretch for tens of millions of light years, almost perfectly empty in comparison to the crowded interiors of galaxy clusters. Others are more complex, containing faint whispers of matter-dim dwarf galaxies, thin strands of gas, and dark matter halos drifting without forming stars. If you could float within one of these voids, you would see almost nothing in any direction. Galaxies would appear as faint smudges on the edge of perception, their combined light barely enough to break the darkness. Yet these voids are not failures of creation. They are the natural result of gravity, pulling matter into the dense regions that eventually formed galaxies and clusters, leaving behind expanses where little remained. Surrounding these voids are immense structures, known as walls, sheets of galaxies, lined up in broad, sweeping formations that stretch across the universe like coastlines around an ocean. These walls are not solid, but they form the outer boundaries of the voids, linking clusters and filaments together. Some are hundreds of millions of light years long, like the Sloan Great Wall, a titanic structure so large it challenges our ability to imagine distances at all. From within a galaxy, such a wall would be invisible. Its scale is so great that no single vantage point could reveal its shape. Only through careful mapping of thousands of galaxies do these structures emerge, showing the universe as a place where matter gathers into enormous sheets surrounding empty space. Within these walls lie superclusters, vast groupings of galaxy clusters, bound loosely together by gravity. The Milky Way belongs to one called the Laniakea supercluster, a region spanning more than 500 million light years. This supercluster contains tens of thousands of galaxies, each one a glowing city of stars drifting in a shared, long-range gravitational field. Superclusters are not static. Their galaxies move over billions of years, drawn toward denser regions and away from emptier ones. Some superclusters are connected by tenuous filaments, while others float in relative isolation. Though they contain unimaginable amounts of matter, even the largest superclusters are only small portions of the overall cosmic tapestry. The filaments that connect these structures stretch across the universe like bridges between islands. These filaments are long, thin strands made of galaxies, dark matter, and diffuse gas, each extending for hundreds of millions of light years. They weave between clusters and across the edges of voids, forming the largest continuous structures known. When astronomers map the positions of galaxies on a grand scale, the filaments appear as glowing veins threading through darkness, linking clusters like beads on a string. In some regions, several filaments intersect, creating nodes where galaxy clusters form. In others, a single filament stretches into the distance, fading into a quiet emptiness. These filaments are the pathways along which galaxies flow over cosmic time, guided by gravity toward denser regions that continue to grow. All of these structures, voids, walls, superclusters, and filaments together form what is known as the cosmic web. This web is the universe's skeleton, the underlying pattern of matter shaped by gravity, acting on the fluctuations left after the Big Bang. On smaller scales, the universe may look random, with stars scattered across the sky in no particular order. But when viewed across billions of light years, the pattern becomes unmistakable. The universe is a vast network of threads and clusters, separated by immense pockets of emptiness. The cosmic web resembles something organic, like the branching of neurons or the delicate structure of veins in a leaf. It is a pattern that repeats across scales, from the arrangement of galaxies down to the distribution of gas, each layer echoing the next. If you could travel along one of these filaments, you would pass galaxy after galaxy, each one separated by unimaginable distance, yet still part of the same cosmic thread. As you drift along the filament, the density of galaxies might rise until you reached a cluster, a glowing knot of hundreds or thousands of galaxies bound tightly together. Beyond it, the filament would continue, curving gently through space until it met another cluster or faded into a wall. And eventually, the filament would end, giving way to a void so deep and empty that the distant galaxies would look like fragile pinpricks scattered across a black horizon. The scale of these structures is so great that the human mind can grasp it only in fragments. Light, which seems swift and unstoppable, takes millions of years to cross even small portions of the cosmic web. Entire galaxies move along these filaments like dust motes riding a current, shifting their positions over timescales longer than the existence of Earth's continents. And yet, despite the immensity, the cosmic web is delicately balanced. It formed from tiny differences in density billions of years ago, with gravity amplifying those differences into the structures we see today. To contemplate intergalactic distances is to confront the universe at its largest. These spaces, silent and nearly empty, make the galaxies themselves seem precious and rare. The voids reveal the scale of isolation. The walls and filaments reveal the scale of connection, and together they form a universe that is both lonely and beautifully woven, a vast web stretching across the darkness, holding everything we know within its quiet, intricate structure. The observable universe stretches outward in every direction like a vast, silent sphere, defined not by walls or edges, but by the limits of what light has had time to reach us. Its radius is about 46 billion light-years, a number that feels almost imaginary when spoken aloud. This means that the farthest light we can see today has traveled across a distance so enormous that even the word distance begins to lose meaning. The universe has been expanding during all the time that light was traveling, stretching space itself and pulling galaxies farther apart. What we see from the earliest times is not simply far away. It is receding from us at speeds greater than light, carried outward by the expansion of space. The observable universe is not the entire universe. It is only the part whose light has reached us in the age since the Big Bang. Beyond it, the cosmos likely continues, perhaps infinitely, into regions forever hidden from our view. The expansion of the universe shapes everything we observe. Galaxies are not just moving through space. Space itself is stretching, carrying them along like dots on the surface of a balloon as it inflates. This expansion rate is measured through what astronomers call the Hubble constant, a value that describes how much faster galaxies recede the farther they are from us. When we look at distant galaxies and measure how much their light has been redshifted, stretched to longer wavelengths by the expansion of space, we see a consistent pattern. The farther the galaxy, the greater the shift, and the faster it appears to be moving away. This pattern allows astronomers to trace the universe's history, revealing that it was smaller, denser, and hotter in the past. The expansion is not slowing down. It is accelerating, driven by a mysterious force called dark energy that fills the universe with a subtle but relentless push. Light travel time adds another layer to this cosmic picture. When you look at the moon, you see it as it was just over a second ago. When you look at the sun, you see light that left it 8 minutes in the past. But when you look at distant galaxies, you are seeing them as they were billions of years ago, long before Earth existed. Light is not instantaneous. It carries the past with it. In this way, the universe becomes a kind of time machine. The farther we look, the younger the universe becomes. Galaxies at the edge of visibility appear as faint smudges formed when the cosmos was still in its earliest stages, mere fractions of its current age. Their shapes are distorted by distance and time, their light stretched and weakened by the expansion, yet they remain visible to us through vast waves of silence. The horizon distance marks the boundary, beyond which light has not yet reached us. It is not a physical edge. Nothing stops beyond it. Rather, it is a limit created by time itself. The universe is 13.8 billion years old, but the horizon lies far beyond 13.8 billion light-years because space has been stretching all the while, photons emitted from the early universe have been chasing us across an expanding medium, and their journey has lengthened as space grew beneath them. The horizon is the point where the universe's age intersects with its expansion. Everything beyond that boundary already exists, but its light has not had time to arrive. It may never arrive, as acceleration continues to drive galaxies away faster than the light they emit can compensate. Beyond the horizon, regions of space recede so quickly that even light cannot bridge the ever-widening gap. When we look toward the earliest epochs of the universe, we encounter not galaxies but a smooth glow known as the cosmic microwave background. This faint radiation is the afterglow of the hot plasma that filled the early cosmos, released when the universe cooled enough for atoms to form and light to travel freely. At that moment, about 380,000 years after the Big Bang, the universe was only a fraction of its current size. It stretched tens of millions of times smaller than it is now, filled with a nearly uniform fog of hydrogen and helium. The cosmic microwave background carries tiny ripples in temperature that correspond to the seeds of future galaxies. These ripples are the earliest structures we can observe, the fingerprints of the universe as it emerged from its primordial heat. The early universe was a place of intense energy and rapid change. In the first seconds, it expanded faster than the speed of light during a period called inflation, smoothing out irregularities and setting the stage for everything that came after. Space itself stretched, carrying quantum fluctuations to cosmic scales. These fluctuations became the foundation of the large-scale structures we see today, the clusters, filaments, and voids that form the cosmic web. In those moments, the universe was so dense that even simple atoms could not exist. Only later did it cool, enough for protons and electrons to join together, creating the first stable matter. From that point onward, gravity began gathering this matter into clouds, forming the earliest stars, galaxies, and eventually the vast networks that fill the cosmos. The scale of the observable universe is impossible to visualize fully. Imagine a sphere containing all the galaxies, clusters, filaments, and voids. We can detect a sphere so immense that every dot of light in the night sky lies deep inside it, nestled within a structure that spans billions of years of space and time. Within this sphere, light travels in straight paths only locally. On the largest scales, it curves through the warping patterns created by mass and dark matter. Even empty space expands, stretching wavelengths and thinning out matter until galaxies grow isolated from one another. The more we look outward, the further we peer backward in time, approaching the moment when the universe itself was born. To contemplate the observable universe is to confront both immensity and fragility. We see only its surface, a thin shell of space-time carved out by the speed of light and the age of the cosmos. Beyond that shell lies a deeper universe, unseen and perhaps unreachable, expanding even as we try to imagine its extent. The observable universe is a reminder that limits are not boundaries but horizons ever moving, shaped by the interplay of time, light, and the quiet expansion of everything that exists. Time, when stretched across the cosmos, becomes something larger than the ticking of clocks or the steady rhythm of days. It becomes a landscape, a vast terrain through which stars are born, wander, flare, and fade. To understand the universe, you must understand not just its size, but its duration, the way it unspools across billions of years so slowly that even mountains and oceans seem fleeting. Imagine compressing the entire history of the universe into a single calendar year, a cosmic calendar where the Big Bang erupts on January 1 and the present moment arrives at the final breath of December 31. In this scale, galaxies form in late winter, the first stars ignite in February, the Milky Way swirls into shape in early spring, and our solar system emerges in September. Dinosaurs appear and vanish in the last week of December. All of recorded human history occurs in the final seconds before midnight, so brief that it could be written as a single spark glowing at the edge of a fading ember. This perspective reveals how short our presence has been and how long the universe has waited for us. Stars themselves follow timelines that are almost impossible to compare to our own. Small stars, the red dwarfs that make up the majority of the galaxy's population, burn so slowly they may live for trillions of years. None have ever died, not one in the entire observable universe, because the universe is not yet old enough for them to reach the ends of their lives. Meanwhile, massive stars, brilliant and blue-white, burn with such fury that they live for only a few million years. They are like cosmic fireworks, short-lived but intensely bright, spending their fuel at a pace that reshapes everything around them. Our sun lies somewhere in between. With a lifespan of about 10 billion years, it is neither a sprinter nor a marathoner, burning steadily in a middle age that has lasted 4.5 billion years so far. When it eventually runs out of hydrogen, it will swell into a red giant, shed its outer layers into a glowing nebula, and collapse into a quiet white dwarf that will slowly cool for eons. When astronomers compare ages across the cosmos, they often speak of epochs, distinct eras marked by changing conditions. Shortly after the Big Bang, the universe existed in the radiation-dominated epoch, a time when photons ruled everything, bouncing and colliding through a hot, dense fog. As expansion continued, matter took precedence, cooling enough for atoms to form, then stars, then galaxies. Now we live in what may be the dark energy-dominated epoch, a time when a mysterious force is accelerating the universe's expansion, pushing galaxies apart faster than ever before. These transitions do not occur on human scales. They unfold across billions of years. And yet they are as real as the shift from day to night, written into the motion of galaxies and the pattern of light traveling through space. The universe's great eras stack like layers in a canyon wall. At the bottom lies the primordial era, the first seconds and minutes when the universe was too hot for structure to exist. Above it rests the era of recombination, when electrons joined protons and light broke free, leaving behind the cosmic microwave background. Then came the Dark Ages, a span of hundreds of millions of years when the universe had cooled enough for atoms to form, but not yet enough for stars to ignite. When the first stars finally formed, they ushered in the epoch of reionization, lighting up the darkness and ionizing the surrounding hydrogen gas. Galaxies assembled, merged, and grew, carving out the cosmic web we see today. Our own epoch sits within this grand timeline, and though it feels like a stable middle chapter, it is only one brief moment in a story still unfolding. Age comparisons across the cosmos reveal a humbling truth. Nearly everything is older than we are. Some stars in the Milky Way's halo formed long before the galaxy itself took shape, more than 13 billion years ago. Certain clusters of stars have remained intact for almost the entire age of the universe, orbiting like ancient lanterns above the galactic plane. The Earth, at just over 4.5 billion years old, is a relatively young world. Life on Earth appeared surprisingly early, within the first billion years of the planet's existence. But complex life needed another 3 billion years to emerge. Humans arrived only within the last sliver of time. An eye blink, a breath, a flicker on the cosmic clock. If the universe were a symphony, we would be the final gentle note at the end of a very long, very quiet movement. Time stretches not only backward but forward into a deep future we can scarcely imagine. In a few billion years, the Andromeda Galaxy and the Milky Way will begin their slow collision, forming a new galaxy with a shape we cannot yet predict. Long after that, in tens of billions of years, star formation will decline as galaxies exhaust their gas. The universe will dim as massive stars burn out, and only long-lived red dwarfs remain, their faint light flickering across a darkened sky. Far beyond that, in trillions of years, those dwarfs will cool into black, silent remnants. Even then, time continues. The universe will become quieter, colder, and more diffuse. Matter will drift apart. Black holes will evaporate. Eventually, even the last traces of light may fade into nothingness. This deep future feels abstract, distant, and almost mythic, but it is as real as the moment you are in now. The cosmos is vast, not only in size, but in duration. It carries ages like layers of mist, overlapping and dissolving, stretching from the first spark of existence to the farthest imaginable horizon. Within this immense timeline, human life is brief yet luminous, a short warmth in a long, cooling night. And though we occupy only a moment, our ability to perceive the vast sweep of time is something extraordinary. We are creatures who can look backward billions of years and forward billions more, aware that we are part of a story older than stars and still unfolding in silence. Time, on the largest scale, is not simply passing, it is sculpting. It shapes galaxies, carves the fates of stars, guides the cycles of birth and decay, and drifts with slow patience toward a future that will outlast every world we know. In that sense, we are not separate from time's flow. We are immersed in it, carried through it, and shaped by it, just like everything else in the universe. There are limits woven into the fabric of the universe, boundaries that shape how much we can know, how far we can reach, and how clearly we can see. Some of these limits come from the cosmos itself, written into its laws with a quiet, unyielding firmness. Others come from the way our minds and senses evolved, tuned for survival on the surface of a small blue planet, rather than for navigating the deep machinery of reality. When we study the universe, we are always pressing up against these edges, trying to measure what lies beyond them, knowing that certain doors will never fully open. And yet the effort continues, driven by curiosity, by imagination, and by the sense that even partial glimpses of the vast unknown are worth pursuing. The speed of light is one of the most fundamental limits, a cosmic speed limit that nothing with mass can exceed. Light travels at about 300,000 kilometers per second, fast enough to circle the Earth 7 times in a single heartbeat. And yet, when measured against the vastness of the universe, even light feels slow. It takes over a second to reach the moon, 8 minutes to reach us from the sun, more than 4 years to travel from the nearest star, and billions of years to cross from one end of the observable universe to the other. This means that everything we see in the night sky is a memory, a message from the past. The farther away an object lies, the older the message becomes, until some galaxies appear as they were when the universe was young and newly lit. Light binds us to a delayed view of the cosmos, letting us see only what has already happened. We cannot witness the present in distant regions of space because the present has not arrived yet. At small scales, the universe imposes a different kind of limit, one born not of distance, but of uncertainty. Quantum mechanics reveals that certain pairs of properties, such as position and momentum, cannot both be known precisely at the same time. This is not a flaw in our instruments or a temporary gap in our understanding. It is a feature of nature itself. The quantum world flickers with probabilities, existing not as fixed points but as likelihoods spread across space. Virtual particles appear and vanish, fields fluctuate, and the smallest scales become a haze of possibility. Even the vacuum is not empty but alive with quantum motion. When we try to measure this world, we disturb it by the very act of observing, adding to the uncertainty rather than reducing it. The closer we look, the more the sharp edges of reality dissolve into a shimmering blur, as if the universe protects its smallest secrets with a veil of fundamental unpredictability. Relativity introduces its own distortions, altering measurements in ways that challenge intuition. Time itself stretches and compresses depending on speed and gravity. A fast-moving clock ticks more slowly than a stationary one. A clock near a massive object ticks more slowly than a clock farther away. These effects are not theoretical or symbolic. They are physical, measurable, and essential to the functioning of devices like GPS satellites. To travel near the speed of light would distort not only the sense of time, but the perception of distance, flattening space ahead and stretching it behind. From certain perspectives, journeys that seem impossible become manageable within a personal frame of reference, even as they remain unreachable from another. Measurement in such a universe becomes a matter of perspective, relative to position, velocity, and gravitational depth. There is no single cosmic ruler, no universal clock. Scale itself introduces ambiguity. When we study the largest structures in the universe, the distances grow so vast that traditional ways of imagining them fail. Thousands of light years become millions, then billions, then tens of billions, and beyond that point, numbers lose their grip on meaning. Even models designed to illustrate scale must take shortcuts, compressing enormous distances into tiny diagrams, leaving us with metaphors instead of accurate visualizations. The same is true at the smallest scales. The jump from molecules to atoms, from atoms to nuclei, from nuclei to quarks, becomes so extreme that each level feels like a universe removed from the one before it. Measurement across these layers becomes a balancing act, requiring new tools, new theories, and new forms of imagination. The universe is too large and too small for any single scale to capture. Our measurements live in between, stretching outward and inward, but never reaching the full span of reality. Human perception imposes its own quiet boundaries. Our senses evolve to detect danger in grasslands, to recognize faces, to follow the arc of a thrown stone. We cannot directly feel the curvature of space-time or see the wavelengths of radiation that fill the cosmos. Our eyes can detect only a narrow band of electromagnetic light, a sliver of the universe's true spectrum. We are blind to radio waves, microwaves, X-rays, gamma rays, and most infrared and ultraviolet light unless we build instruments to translate them into forms we can perceive. Even then, we rely on color maps and false images to glimpse what lies beyond our natural limits. Our sense of time is equally limited. We feel minutes and hours, not millions or billions of years. We judge size by the span of our arms, not by the width of galaxies. To bridge these gaps, we use analogies, scaling, and mathematics. But the universe always exceeds our intuition. In the face of all these limits, measurement becomes both an act of humility and an act of ambition. We acknowledge that we cannot see everything, cannot know everything, cannot measure everything with absolute precision. Yet we still reach outward, building instruments that extend our senses, theories that stretch our imagination, and experiments that probe the edge of the possible. The speed of light remains fixed, but we measure the faintest rays arriving from billions of years ago. Quantum uncertainty blurs the smallest scales, but we map their probabilities with stunning accuracy. Relativity bends time and space, but we use those bends to understand the cosmos more deeply. And even though our perception is limited, our curiosity pushes us beyond what our senses can grasp. In this way, the limits of measurement do not confine us. They shape the way we explore. They remind us that knowledge is a journey, not a destination, and that even partial understanding can illuminate vast regions of the unknown. The universe is immense, mysterious, and sometimes inaccessible, but within its limits lies a profound sense of wonder, the feeling that we are touching the edge of something immense, even if we cannot see the whole. In the quiet moments when you look up at the night sky, it becomes clear that the universe is not just something outside of us. It is something we are woven from, something we carry within us in ways both literal and poetic. Every atom in your body was forged in ancient stars, scattered through space in waves of light and debris long before Earth existed. When you breathe, when you think, when your heart beats, you are participating in a story billions of years older than the mountains and oceans. And yet, from your small vantage point on a spinning world, everything feels close. Your worries, your memories, your hopes, your challenges. But scale can change that feeling. When you allow yourself to drift into the vastness, to imagine distances larger than imagination and timescales older than thought, something in you loosens. The universe grows, and the weight of your world grows lighter. Your place in cosmic distance is not at the center of anything, nor is it on the edge of some immense structure. You are inside the Milky Way, halfway from its center, orbiting in a quiet spur between two major arms, drifting through a sea of stars that stretch in every direction for tens of thousands of light years. Around you lie clusters, nebulae, and ancient remnants. Far beyond that lie other galaxies, spirals, ellipticals, dwarfs, and the cosmic web that binds them together. You are surrounded by distances so immense that even light, the fastest thing we know, needs lifetimes to cross them. And yet you occupy a specific place within this whole, not arbitrary, not meaningless, a precise position in a universe that does not assign importance but does allow for presence. You exist inside a structure that is still growing, still moving, still unfolding. You are carried within it, not separate from it. As you drift through these thoughts, the idea of big and small begins to blur. These words belong more to human perception than to physics. A mountain feels enormous because your body is small. A molecule feels tiny because your senses cannot feel its edges. But the universe does not judge size. A star is not grand because it is large. A quark is not insignificant because it is small. Each plays its role in the structure of everything else. What we call big and small are simply markers of our own experience, applied to a cosmos that does not measure itself against us. When we release the illusion that scale defines importance, a kind of quiet understanding settles in. The world becomes gentler, less sharp, as if the edges of our anxieties soften when placed against a backdrop of billions of years and billions of light years. The comfort of insignificance may sound like a contradiction, but it is one of the deepest gifts the cosmos offers. When you see yourself as the center of everything, every problem becomes immense, every moment becomes heavy. But when you see yourself as a part of something vast, your difficulties, while still real, lose the power to eclipse everything else. The universe has carried stars through life and death, galaxies through collisions and rebirths, atoms through billions of years of motion. It can carry you too. Knowing that your life is a small, warm point of light against an endless backdrop is not diminishing. It is freeing. It means that you are allowed to rest. You are allowed to drift. You are allowed to be one quiet moment in a story far beyond your own. And yet insignificance does not mean invisibility. You are the universe becoming aware of itself, a fleeting consciousness looking back across the dark from which it came. In all the billions of galaxies, in all the trillions of stars, on all the worlds we cannot yet see, the chance that your exact pattern of atoms and memories would form is unimaginably small. And here you are, not at the center, but within the whole. Not the point of everything, but part of everything. Your existence is both ordinary and extraordinary, fragile and enduring, temporary and eternal, in the sense that you carry atoms shaped by ancient forces and will one day return them to the cosmic sea. Scale creates calm because it reminds us that we are not required to hold the universe together. We are not responsible for every shift of fate or every ripple of time. We are passengers in a grand unfolding, held by the same gravity that holds stars and galaxies in their quiet orbits. When you imagine distances too large to cross and times too long to count, your breath slows, your thoughts stretch, the tightness in your chest relaxes. Nothing in your day feels quite as overwhelming when compared to the arc of a galaxy or the lifespan of a star. This is not to dismiss your experiences, but to place them in a wider frame where they can settle gently instead of pressing sharply against you. In the end, finding yourself in the cosmic scale is not about shrinking your life until it vanishes. It is about seeing your life as a single note in a vast and beautiful composition, not the whole melody, but a necessary sound within it. You are here for a moment, luminous and breathing, resting, inside a galaxy that will continue long after your story has finished. And still, this moment matters, because it is yours, because it is happening now, because the universe, in all its silence and size, has allowed this brief flicker of awareness to exist. As you settle deeper into the quiet, imagine yourself drifting outward, not to escape, but to see clearly. Through the atmosphere, past the moon, past the planets, past the spiraling arms of the Milky Way. Imagine rising until the entire galaxy glows below you like a swirl of soft light. Then rise further until galaxies blur into threads, and threads into a web, and the web into a faint shimmer across the dark. Somewhere in that vastness, a single world spins. Somewhere on that world, you breathe. Somewhere in this moment, you rest. And as the universe continues its slow, graceful turning, you are part of it, small, yes, but luminous. Quiet, yes, but real. One warm point of consciousness in the great, gentle sea of cosmic scale.